you.
Very good morning and assalamualaikum to everybody. Today, I would like to welcome you to the second session, to the second day of iNuSTEC 2020. We are honored today to have Professor Dr. Craig Mariano brought to you from Department of Nuclear Engineering, Texas A&M University from USA. Prof. Mariano will be giving the talk today, the keynote today on the role of nuclear science professional in security and emergency responses. Without further ado, I would like to invite Prof. Mariano to give his talk. Please proceed, sir.
Thank you very much. I appreciate the introduction. Hello, everybody. First, let me say thank you very much for allowing me to address participants at the International Nuclear Security Technology and Engineering Conference. I know we all wish we could be there in person. For myself, I've never been to Malaysia, and I was looking forward to visiting your beautiful country for the first time. Hopefully, there'll be other opportunities for me in the future so I can visit your country and meet you in person. But in the meantime, I hope that we can all stay safe during these challenging times. Now, any career in the nuclear sciences can be fun and exciting. Many careers in this area involve research in industrial applications, the medical field, and even in warfare. This research drives innovation, creating new technology for the betterment of society. However, there is much more to do in nuclear science and technology than just research. In fact, in the last 50 years, new applied careers have emerged that require talented, intelligent, and trained people that understand radiation. And that's what I hope to give you a small introduction to today, talk about the history behind where we are at in these careers and how we got there and where we hope to go in the future. Next slide, please. Now, in preparing for this talk, I found out that Willem Röntgen, pictured on the left of the screen, discovered the X-ray almost 125 years ago to the day. On November 8, 1895, while conducting experiments on Crookes tubes, Röntgen noticed that he could cause a phosphorescent screen to actually glow, even though his tube was being covered. He called these X-rays because he didn't know what was actually causing this, but the name stuck. I'm sure you've seen the famous photo of his wife's Bertha's hand that was X-rayed. This is one of the very first known X-rays ever, and you can actually see her wedding ring on her ring finger on her left hand. And for his work, he actually earned the very first Nobel Prize in physics in 1901. Now, for me, it's here that nuclear science really began. The research was new and exciting. Things were being discovered left and right. New uses for radiation were being discovered, new materials. Really, a new science was developing right in front of our eyes. And we all know the greats of the time. We have Planck, we have Curie, we have Bohr, we have Thomson, and we have Einstein. And this is just to name a few, and I realize there's so many more, but these were the names that I could think of and the exciting people of the time for me. Next slide, please. And then from the discovery of the X-ray, 40 years of scientific revolution takes place. Nuclear science and technology influence physics, industry, and medical technology. What is most exciting for me about this time is that fundamental experiments were being performed that increased our understanding of the universe. These experiments that were being performed then were brand new. Today, they're just old and they're basic. But at the time, this is extremely exciting. I find it exciting to this day to do the experiments that Thomson did or Geiger and Mueller. But what is most exciting to me about this time is that it's the fundamental experiments that are explaining the universe. And the fundamental radiation particles are being discovered at this time. Alphas, betas, gammas, neutrons are being discovered and classified. They're seeing how they react with matter, what they do when they interact with matter. This slide is just showing a few areas like an early medical imaging facility, which is over on the left. You have Bohr's atom, which gave us an early understanding of the structure of matter. People were convinced of the healing properties of radiation, and you could buy a ceramic jug that I have pictured on the bottom left that leached radium into water, and people could drink radiated water. They thought this provided some sort of cure-all. At the bottom left, you could actually see a real invention where X-rays were used to fit shoes. I wouldn't recommend that right now, but it existed and it was out there. You had incredible machines that were being built to understand the physics of the particles that were being discovered. Pictured at the bottom center is the cyclotron by O.E. Lawrence. I actually worked on this cyclotron as an undergraduate. It was eventually moved from Berkeley to UC Davis, where I did my undergraduate in the 90s. That's the 1990s, not 1890s. And it was exciting for me to work on something that Lawrence actually worked on. And of course, neutron activation was being introduced during these early years by Fermi, where he was making new radioactive substances by bombarding materials with neutrons. It was an extremely exciting time, an extremely fun time. I think as scientists during this time, it just would have been just a lot of fun for me, at least. Next slide, please. Now, of course, you can't talk about nuclear sciences without mentioning the Manhattan Project. And despite what it created, it also helped drive innovation. Pictured here is a depiction of the graphite pile where the first sustained chain reaction occurred in a squash court at the University of Chicago in the United States. We also can't forget that along with the development of the nuclear weapon came other advances in technologies. What you're seeing in the bottom right is one of the very first computers that was used to help design the weapons. This computer here filled several rooms worth of space and probably does not have the computing power of an iWatch. But technology was born during these times. I'm just mentioning computers, but you have transistors, you have electronics, you have photography. Just really impressive innovation because of the nuclear weapon. Next slide, please. This brings me to one of my topics of an applied nuclear science field. Now, up until the 1940s, I don't really know what security measures were taking place. But as it became clear what you could do with radiation and radioactive material, security and secrecy became an issue. Specific security measures were put in place because of the threat we understood. And the threat was an adversary or adversaries wanting to either take the technology or the material. And we had to ask the question, how to protect it. Now, at the time, and even today, when we talk about security, we might think of just guards with guns. In this, I'm showing you the guard gate at Los Alamos. I'm showing you a pedestrian entry where a guard is watching ID badges. In the bottom left, cars are being searched at the plant at Oak Ridge, Tennessee. In the center bottom, we have double barbed wire fence around the facility protecting it. We have ID cards I have two famous people in the Manhattan Project. One, John von Neumann, who was probably one of the most fascinating and smartest mathematicians of the 20th century. And then you have right next to him Klaus Fuchs, who was an actual Russian spy who actually gave the early designs to the Russians. And then the very, very bottom, you have a sign telling people to be aware of your surroundings, be aware of what you do here, but do not think about or even talk about what you do outside of the gates. And for the next 25 to 30 years after the creation of the atomic bomb, nuclear security is primarily protecting against a state threat. It's the Cold War, and we're worrying about weapons technology getting out to other countries. During this time, the International Atomic Energy Agency is created, and it promoted the peaceful use of nuclear technology without the development of the nuclear weapon. And it allowed nuclear science and technology to be expanded throughout the world and controlled so development of nuclear weapons would hopefully not occur. But by 1970, 6 countries had built and tested a nuclear weapon. And the idea of someone using a weapon that is not used in war was just not even thought of. So therefore, nuclear security was really being focused on the facility and not really looking at anything else. Next slide, please. So in the early 70s, things began to change. In the United States, law enforcement would sometimes get notes, and these would be blackmail notes saying that, hey, I have a nuclear weapon. If you don't pay me, $600,000 right now, I'm going to set it off, and it's going to kill everybody in the city. And this was what they called nuclear extortion. This is actually a picture of an article that's taken from Time magazine in 1970. In one case, the letter included a rough sketch of the design. Now, law enforcement didn't know what to do with this sketch, so they sent it to the FBI, or Federal Bureau of Investigation. They don't know what to do with it, so they send it then to weapons scientists. And the weapons scientists, they look at it, they scratch their head, they try to figure out, is it real, is it not? And they begin to think, this could be a credible threat. So if it's real, how do you detect it? Can we even detect it? So now this type of threat had been considered already, even at the end of World War II, when Robert J. Oppenheimer, who's the leader of the Manhattan Project, was asked in a closed-door Senate hearing whether 3 or 4 men could smuggle in an atomic bomb in a briefcase and blow up a whole city. And he actually said it is possible. And the senator asked, well, then how can we detect? How can we find such a device? And all Oppenheimer could say is a screwdriver. And what he's pretty much saying that these things are hard to find. They're hard to locate. And if you want to be 100% sure to find it, you will need a screwdriver to open up every crate, every box, every suitcase to find the bomb or the components to make a bomb. And believe it or not, up until 1970, not much had really changed. A screwdriver was probably your best bet. But people began to ask the question, can we detect something? How can we detect it if there is really something? Now, during one of these threats, scientists were actually deployed. And when I say scientists, I actually do mean nuclear professionals, not commandos with guns. It was scientists who had built and designed these weapons, who had built and designed radiation detectors. They were deployed with instruments that they had built to try to detect a potential bomb in a public setting. Now, this first event was not very well organized, unfortunately. During this first deployment, the equipment went one place, the team went to another city. Luckily, eventually, the equipment and the team met up, and it is about that time that they realized that this extortion was actually a hoax. But it could have been real, and it worried the leadership in the United States to the point that we created a specialized team called the NEST team, or the Nuclear Emergency Search Team. And it was formed around 1972-ish, and it was a top secret team that could go out into the public without being noticed and search for illicit radioactivity. And as I mentioned, it was classified, but really it wasn't classified for very long because something called Operation Morning Light occurred. And in this case, a Russian satellite that had plutonium on it lost orbit, and it actually came crashing down all over Canada. The Canadians were concerned about the distribution of plutonium in the environment. They didn't really have ways to look for it or find it. So our president, who was President Gerald Ford at the time, talked to the Canadian Prime Minister and said, hey, we have this team. They are specially formed professionals with special equipment designed specifically to find nuclear material in the environment. Do you want their help? The answer was yes, and it was at that point that NEST became an unclassified program. And it existed in some form or shape between 1970, all the way, well, they changed names here and there. I was actually part of the NEST team in my professional career in the early 2000s. But still, even after we had these nuclear, hoaxes, these nuclear extortion threats, the idea to the public that a real threat is possible really never hit. It was never really a concern for almost 25 years. Next slide. And it was September 11th, 2001 that really changed things. Osama bin Laden, with just a couple of planes, destroyed 2 buildings in the middle of New York City. It was known that he was actually looking for special nuclear material on the black market. He was a millionaire. He could afford it. What happens if he did get it? What happens if he actually had the scientific expertise within his organization to build a nuclear weapon and to deploy it? It could have been, in this case, it was planes. Could it have actually been a nuclear weapon? And this worried the public. It worried our leadership. It worried worldwide leadership, in fact. Next slide, please. Now, because 9/11, this is what nuclear security really looks like in an applied fashion to this day. It's at borders, it's at shipping ports, it's in the air, it's on the water, it's on the ground. It's in handheld systems that are specially designed and made for untrained professionals to use. It's in backpacks. The bottom right picture is actually a real radiation detector backpack. In most cases, the people who are using and operating these systems are not really trained nuclear professionals. They are law enforcement. They've gone through limited training. They understand what they're doing. But in some cases, especially the early days when I was training people to do this, they were very concerned about the radiation that they were detecting. Would the radiation that they're detecting hurt them? And you had to do a lot of training to kind of to smooth out their fears. And that's why, in a sense, why nuclear professionals like myself are needed in this field. Nuclear professionals like you, perhaps. So nuclear scientists and technicians are needed in this field, and they're not just in the lab. They're also needed to fill deployable positions to help advise, help train, and help operate equipment in the field, and they work side by side with the guys with guns. As a scientist, you're probably not going to carry a gun, but you're going to help and be out in the field. Now, these pictures that I show here are at shipping ports, where you see in the top left large radiation portals scanning trucks as they leave a shipping port. They're at borders, which is the center picture. They are on helicopters. Those are actually 2 very large radiation detection pods that are hanging off the helicopter on either side. We drive detectors around in cars that look like normal cars, but we are able to drive these around without being noticed and look for radiation in the environment. We have specialized instruments that are now commercially available. Between 1970 and really 2001, these specialized instruments were only in the hands of the government and in the nest teams. But after 9/11, after the threat of nuclear terrorism came about, large investment came out, and now specialized instruments are being built and created for untrained users. And you're seeing that in the bottom center section, where customs officials are scanning a cargo container, and again, the radiation backpack. Next slide, please. So in nuclear security now, nuclear professionals, scientists and technicians are needed. And I know I've been talking about an applied field, but they are needed in research. New detection materials are needed to this day, not just for gammas, but for neutrons. New identification and localization algorithms are being created and are useful in this profession. And of course, with the development of artificial technology and big data integration, this is becoming very, very large in how you can develop nuclear security detection systems to help protect the public. And the people that we need, are all over. You need them in law enforcement. You need them in the military. You need them in customs. You need them in a position to help advise public officials, because the public officials who are going to be in charge of protecting the public from the harm that might be given or produced by radioactive material are not experts, and they needed to be advised, and people who are specialized in radiation are needed for that. Next slide, please. Now, a subset of nuclear security, and I wanted to mention this briefly, is something called international safeguards. And it came about around 1960 as part of a process that is operated and organized by the International Atomic Energy Agency. Now, the purpose of safeguards is to deter the spread of nuclear weapons by the early detection of the misuse of nuclear material and technology. And this is accomplished in many ways with on-site inspections where you can take measurements either with handheld detectors, or you can take samples of soil or swipes of dust on equipment, or even take samples near equipment. It is also done with remote monitoring systems. And these remote monitoring systems can be in the form of radiation detectors. They can be in the form of cameras. They can also be in the form of physical locks. And this technology that is being used in safeguards for the last almost 60 years still requires research, still requires an investment. And you're going to need not just people doing the research, but you're going to need inspectors in the field. And you're going to need scientists and technicians in the labs at the IAEA to analyze the samples and maybe even the data that you take in the field. So this is an area of nuclear security and science that I was not aware of in school, and that's why I bring it up, because I thought this is something, if you're not aware of it, you should be made aware of. This is something that is a fun and exciting job that is being done by, there's 2,000 inspectors, I think, today in the IAEA that go out all over the world to inspect facilities. Next slide. Now, nuclear security and safeguards are on the side of prevention. Sometimes we call that in the United States, we are pre-boom, before the event occurs. That is what security and safeguards is trying to do. But you must deal and accept that there are going to be consequences if something happens, you lose control of that material, either on purpose or an accident happens. So if prevention fails, you need what we call consequence management. You need to deal with the consequences. And they can be both large and small scale incidences. The picture on the bottom, or on the left, is of 3 Mile Island. I'm sure you all are aware of it. It was an accident that happened in 1979 in Pennsylvania in the United States. It was a minor release. However, the United States did not respond well to it because at the time we did not believe a nuclear meltdown or a problem with a nuclear power plant could happen. Therefore, if you don't believe something could happen, why train for it? Why be prepared for it? So luckily, it was a small release, and we learned lessons from that. And because of the lessons we learned that you need trained individuals to be prepared for it, we created a consequence management program in the United States that is still around today. It is an extremely robust program that we train annually for different events. I'm still part of this team on an advisory role. And people are still needed. I was just talking to a scientist today who says we need young people in this profession. And of course, we have Chernobyl. We also had Fukushima. Now, these are accidents. They are not didn't happen because of purpose misuse for the most part. I can say that, the United States did not assist in the response to Chernobyl, but we did actually assist in the response to Fukushima. We had a deployable team on the ground in Japan for several months following the incident to help scan the countryside and go through cities and to help evaluate the radiation to assist the Japanese government. But in both cases, I would argue that both Russia and Japan really didn't believe that anything could happen, and maybe they weren't as prepared as they could have been. And I recognize that Fukushima just occurred with a tsunami, and they were dealing with that. But I don't think they had the equipment even available to fully evaluate what a major release could do. So the United States was able to provide that and provide personnel to look at that. The bottom left picture is of a small scale release at a facility where people are just trying to clean it up and evaluate how bad it is. And then the bottom right is Goiânia, Brazil, where in the 80s a cesium source that was at an abandoned medical facility was stolen by junk dealers, brought to a junkyard where it was punctured, and then they spread cesium-137 throughout the junkyard and throughout a small neighborhood in a house. Several people died, but Brazil, found out about it, and the government had to respond. And it was a major response. But again, this is dealing with the consequences, training for it, understanding it. And this could be a very expensive process. Next slide, please. Now, this is just to kind of give you a rough idea of the complexity and timeline that might occur following an accident. In the bottom left is the event is essentially occurred, and it could be a very small event to a spill at a facility, a car wreck on a road that contains where the shipment contains radioactive material, but it's radioactive. The local responders don't know what to do, or they need help and advice. In the United States, we have something called the CMHT, which is the Consequence Management Home Team. I apologize for all the acronyms, but in the United States, we live for acronyms. And the Consequence Management Homes Team is available by phone, on computer, or collaborative software like WebEx or Zoom or Microsoft Teams. And they can help advise locals on the complexity of the situation that they are facing. If the locals are overwhelmed and need more support, that's what the next dot above that little house on the left means between 0 to 6 hours. Who is responding to the incident? And it could be state and local hazardous material teams. If they are overwhelmed and they need more help, then they can rely on something we call the RAP team, or the Radiological Assistance Program, or the civil support teams, which are teams specifically trained to respond to radioactive material incidents. And they can deploy out, and they're very small, they can move very fast, they can go out anywhere in the United States because they are regional, and help local teams with problems. If still more support is needed, between 6 and 12 hours, our aerial measurements system, or AMS teams, will show up. These are airborne radioactive detective systems that can scan large areas of land very rapidly and give you a very good idea of the type of radioactivity you're talking about and the amount of dispersion that has occurred. And then the rest are just other teams that can kind of show up and complement or supplement the response. And within 24 to 48 hours, all the federal assistance that would be needed for a major event has at least showed up. And it forms what is called the Federal Radiological Monitoring and Assessment Center, or the FERMAC. And it can be several hundreds of people, but they have the ability to scientifically assess the situation. They have equipment that local responders might not have. They have technicians that have expertise that local responders might not have. So they are going out and sampling, working with locals to find locations of concern. They're taking measurements, and then the scientists within the FERMAC or even at the home team are evaluating the measurements and trying to determine the hazard that has occurred. Next slide, please. Now, consequence management is essential. You need to plan for the worst because you do not want to try to plan for the worst during the actual emergency. And it is very, very important that you train not only the first responders, but also the public officials. You don't want the public official to learn about the word radiation for the first time during a radioactive response. So you need to make sure that people are trained regularly on what to do and how to do and deal with radioactivity. And I have this line here. It's a firehouse without ever having a fire. And sometimes that's how consequence management is viewed. It is very expensive to maintain training and equipment and people. And it's like having a firehouse where you hope that a fire never, ever occurs. But it is essential to have at least the foundation of that around, and you have a core team that is ready to respond and help individuals. And that's what these pictures are showing, people training for decontamination, That the center picture is an emergency operations center where people are getting a brief. You see in the bottom right where people are being scanned for radioactivity. The people who are not in personal protective gear are probably evaluators. They're not part of the emergency. That's why they are not in PPE. And then the bottom is a depiction of what we call a briefing product produced by the National Atmospheric Release Advisory Capability, which is an atmospheric dispersion model group in the United States, which can produce map products showing the potential extent of plumes based on models. And this is based on either readings you've taken on the field or what you know about the source term, what was released. Next slide, please. Now, hopefully, you can see where trained nuclear science professionals are needed, not just in research, but in these fields that kind of have sprung up because of what nuclear science has given us. We need people in consequence management. We need people in what I've called nuclear security here. In most cases, some people call this what they call incident response, but it's dealing with the stuff outside of the facility. And there are lots of opportunities out there that people can take advantage of, and it is a fun career. I've had a really invigorating career, and I've really loved a lot of it. And I'm happy that I've gone to university and I can teach the next generation about it and what and how to do nuclear security and emergency response with radiation. And that is the end of my talk. Do you have any questions?
Thank you, Prof, for a very, I would say, an eye-opening situation on nuclear security. On your desktop, you can see some questions that is being asked on the chat from the chat room. Could you see?
I have the chat open, but I do not see any questions.
Okay, if that were the case, then we have about maybe 8 minutes more. So perhaps I would like to ask some questions for you. Is that okay?
Yeah. At first, I want to apologize if I talk too fast.
No.
It's an exciting field for me, and I sometimes get really excited and talk fast. So I apologize.
Yeah, I can understand what you were saying because my field is physics. I'm trained in nuclear physics and particle physics. So I appreciate very much your talk. And it's very relevant.
Thank you.
Okay. With regard to the present COVID-19, you know that nuclear, in nuclear reactor, nuclear power plants especially, the contingency mitigation plan is very comprehensive and very extensive. How can that be adopted to the current COVID-19, or should the present SOP, standard operating procedure for nuclear power plants, should be enhanced for the COVID? Do you think?
I'm sorry, I don't really understand the question. I apologize.
You know, now we have the COVID-19 situation, pandemic.
Uh-huh.
The mitigation plan for nuclear is very extensive. Nuclear power plants. So how can that be adopted to help the COVID-19?
Oh boy, that's a very tough question. So you're asking how can some of the things that we do to stop infections within the nuclear power plant be kind of adopted in general to help protect
It's the other way around.
Okay.
Because in nuclear power plants, there are procedures that we, for example, shielding, time exposure, and distance. This could be applied to the COVID-19 prevention.
Yeah, It's actually funny that you say that because in the United States we're in the middle of a very large upswing, and I described actually it reminds me of radioactive contamination. That if you are smart about the environment that you're in, if you are wearing your personal protective gear, your mask. If you want to wear gloves, you can wear gloves. You maintain distance from people. You reduce the time around people. Yeah, and luckily, knock on wood. That's an American saying. I'm sure I know, but my family has been safe. I have been safe. Nobody's been infected yet. But I think of it really as a problem of radioactive contamination. Treat it like that, respect it, and hopefully you'll come out on the other side not affected by it.
Yeah. On the other hand, you said that nuclear scientists or nuclear engineers should also be given the chance or the opportunity to be part of the law enforcement team, right?
Yes.
Okay, it was ironic because here in Malaysia, we have University Technology of Malaysia, which is producing nuclear engineering graduates since 2014 now. So we have many nuclear engineers which are doing non-related to nuclear jobs. So if for example this nuclear engineers is employed as enforcement officers, they are more effective.
Oh yes.
That's one, and the other thing is that you also mentioned about Manhattan projects.
Mm-hmm.
Yeah, so to me, it was the Manhattan Project on the good side. It triggers the research in nuclear, in computing,
yes.
World Wide Web, and so on. But on the bad side, there's always two sides of the coin. What do you say?
Yeah, I agree. I think the technology that came out of the Manhattan Project, not just the bomb, but I think there was a lot of good that came out of that program that was not related to the military. I think of when I talk about sometimes bomb testing, I talk to the students about photography. The idea of being able to take a picture of something that is dark and then all of a sudden brighter than the sun, and then then it cools down, and the strobe light technology was developed in high-speed photography. Medical treatments. I mean, it's phenomenal what came out of it.
For your information, in Malaysia, we have previously Datuk Razak Abdul Habib, who was a survivor of Hiroshima and Nagasaki.
Wow.
So where he used to go around telling people about this. So I'm from Malaysian Nuclear Society as well. So the first extensive talk that he gave, he told us about his experiences. He was actually under the pile of some rubble, so he came out unscathed. There were about 3 or 4 of them, so he survives. And after we asked him, what do you think about nuclear? He says, nuclear for science is good. He has no objection. So to me, to a person who has undergone that kind of experiences, he said, nuclear for science, I have no problem with nuclear for science. So what do you comment?
It's amazing.
Should we include the ethics of nuclear applications to the nuclear engineers and scientists education?
Definitely.
Then we have no worry. Would you like to add more? We have about, I think, 1 or 2 minutes.
I'm actually, I just want to thank you very much. I really wish I could have been there in person. I've had opportunities to be in Indonesia, but never Malaysia. And I hope someday to come and see you in person and meet you as well. And good luck the rest of the time.
Yeah. Okay, so we are very, very honored to have here with you, Orway from US. Okay, there's one question. Prof, I would like to know your opinion about the security of remote monitoring with regard to the current involvement of nuclear security threats.
Remote monitoring is what done by the IAEA is extremely secure. They have security standards that exceed the World Bank standards, and so we sometimes joke that if somebody could break the World Bank, they're going to be more interested in getting the money from the World Bank than any nuclear security information. So I know that the information that's transferred is very secure, and it's really hard to spoof that information, at least that I know of.
Okay. If there is no further questions from the participants, on behalf of the organizing committee, I would like to thank you very much for spending your time with us, and it's very, very good actually. It is an eye opener to us in Malaysian with regard to your lecture. So can I invite the participants to give appreciation to Prof. Moreno in the usual way? Okay, fine. See you.
Thank you. Bye.
Bye. Oh. Welcome back, ladies and gentlemen. And now we are in the invited speaker session. We are lucky today to have Miss Nur Aslinda binti Anwar she's doing her PhD in the Texas A&M University, to give her talk on the application of non-negative least squares in gamma source imaging for nuclear security. Without further ado, I would like to invite Nur Aslinda to give her talk. Please.
Assalamualaikum and good morning, Malaysia. My name is Linda Anwar. I am a nuclear engineering PhD student at Texas A&M University. Today, I am going to talk about my PhD research, which is on the application of non-negative least squares to image gamma source for nuclear security. Let me start first with the motivation of this research. Close to 3,500 incidents have been reported in the span of 25 years involving radioactive and nuclear material trafficking. So this is an average of about 140 incidents per year. So though some incidents were actually found to be harmless, it is also very concerning to know that these actually happened. So there's a high attraction for radiological sources to construct radiological dispersal devices, also known as dirty bombs, And this is one of the reasons why border crossings and shipping ports are equipped with monitoring systems. But secondary monitoring systems would be useful to verify the alarm set off by the primary monitoring system. It will also help personnel on duty to make decisions on how to handle the suspected radioactive material. So in this research, we are interested in designing an imaging system specifically for gamma source that acts as a secondary monitoring system. So the research objective is to develop a design concept for imaging gamma sources using compressed sensing principles. The resulting system is expected to localize the image radioactive source and provide its shape information. So this can be achieved by first conceptualizing the gamma imaging system, and then design an initial proof of concept using Monte Carlo simulations. We would then build the apparatus based on the simulation results, and then do testing and try to match the experimental results and simulation results. And based on these, we would then modify the simulation model or the experimental design to validate the results. And finally, we would then propose an improved design or technique for the gamma source imaging system. Compressed sensing has gained popularity through its success in improving signal processing efficiency in various applications such as facial recognition, photography, network management, radio astronomy, and so on. So I like to use the concept of image compression as the starting point to understand compressed sensing. So how does image compression work in general? So we can apply one of the popular methods called transform coding to an image X, which will turn X into a sparse or compressible representations of signals. So what is sparse, you ask? Sparse means that for a signal of length n, we can represent it with only k non-zero coefficients, and k is way less than n. And compressible representation means that the signal is well approximated by a signal with only k non-zero coefficients. So therefore, let's say we have an original image of a cute little kitten here, X. We can perform transform coding on it, and this will give a different vector X naught. So this X naught is now the sparse version of X. So they are literally the same thing, only represented differently. And almost every element in X is non-zero. As you can see, there is a lot of different colors for each pixel. But since X naught is sparse, only several elements have non-zero values. The rest are zeros. Therefore, the image can be stored more efficiently by only saving the non-zero coefficients and also the locations of these non-zero coefficients in the vector or matrix. So this is basically how media formats such as JPEG, MP3, or MPEG store our media files in a smaller size. Compressed sensing tagline is basically making do with less. So rather than sampling at a high rate and then compressing the sampled data, we would like to directly sense the data in a compressed form. So that is at a lower sampling rate. However, lower sampling rate means lower number of measurements, and this is classically not possible to solve because then you would have more unknowns than the number of equations. However, it turns out that we can solve this by looking for the sparse version of X, which is X naught. So to solve this relation, we can find the sparsest solution or the sparsest representation of solution. So this can be done by minimizing the L0 norm of X, because L0 norm is just the number of non-zero elements in the vector. However, this process of looking for the number of non-zero elements in a vector is an NP hard problem. So it is impractical for computations. However, the good news is that minimizing L1 norm estimates the minimization on L0 norm very closely. And to solve for a minimization of L1 norm, there are a lot of efficient algorithms that exist. And another interesting finding in this topic is that if X can be recovered by L1 minimization, then X is the unique solution to this AX equals B relation. Therefore, if X is non-negative and sparse, and in our research, we expect that the image consists of only non-zero elements. So the use of non-negative least squares will typically give the same solution. So instead of minimizing the L1 norm of X, we can actually minimize the L2 norm of this relation instead, with the constraint that X is equal to or equals to or greater than 0. And this can be achieved by using the LSQ non-neg function in MATLAB to perform the image reconstruction. It is also important to note that one of the requirements for this to work is that the matrix A must have randomness as its property. So in this research, the matrix A consists of random combination of elements 1 and 0. I'll explain in a minute how I physically represent these values in the actual setting. So I won't go into the details of the long design process, but this is the final design of the proposed system based on multiple iterative MCNP simulations, as well as taking into account other constraints such as the availability of equipment and hardware, as well as the cost of the materials used. These are some illustrations using the MCNP visual editor program. The system consists of a huge tank. It's actually a 250-gallon rectangular tank filled with water with an 11 by 11 PVC pipes arranged together as a grid, and this is called a collimator. So the collimator is what matrix A represents. So one random combination of air and water in the collimator is called a configuration. As I mentioned before, it consists of only two values, zeros and ones, which are randomly generated using a Python code with an open factor of 50%. So in other words, for each one configuration, 50% of the pipes are filled with water and 50% with air. So the matrix A is translated to the pipes by assigning the value 1 to air and 0 to water. So the reason being is that when there's air in the pipe, this represents the photon being able to travel through the pipe to the end of the tank to get detected. And mathematically, this can be represented as 1. And 0 represents the attenuation of photons by water in the pipes. Underneath the tank are 6 Geiger-Müller detectors positioned in a radial arrangement as shown here in this picture. So the GM tubes are modeled with neon gas in them, along with the aluminum casing with the specific dimensions as shown in the specification sheet. So the F4 tally, which is the cell flux tally in MCNP with several modifier cards, was utilized to estimate the detectors counts. The expected counts from the MCNP simulation can be determined by multiplying the measurement time, the detector sensitivity, and the exposure rate, which is essentially obtained from the F4 tally in MCNP simulations. So in my simulations, the F4 tally has the unit of RAM per hour because of the tally modifier DE and DF. However, by including the photon strength, the unit conversion, and the sensitivity of the detector in the FM card, the final value reported in the MCNP outputs would end up being the expected true count rate with a unit of counts per minute. So this is pretty convenient, as I can then just multiply the F4 tally from the MCNP outputs by the measurement time, which is 15 minutes, to get the expected counts. So the simulated counts are then represented as matrix B And the relation AX equals B is then solved using non-negative least squares in MATLAB. So this process is called the image reconstruction process. So these are some of the examples of simulation results with a 0.4 millicuries cesium-137 point source in 4 different positions. So I have also done it for a ring-shaped source, and that was also successful. However, I am focusing on the point source shape as that is what is available for me to do experiments with. 100 measurements corresponding to 100 configurations were used to produce these images. Again, to remind you, the total pixels is 121 as we have 11 by 11 PVC pipes. And 100 measurements is less than the total number of pixels. So the results here are expected, as we can see for the positions in which the source is placed directly on top of the collimator. The images are clearer, mainly because the source is closer to the collimator, hence closer to the detector at the bottom of the tank. But for these 2 positions here, the source is placed about 11 inches above the collimator. So that represents the longer distance between the source and the detectors. And because of that, we expect to see more scattering, and that's going to result in some unwanted artifacts, such as shown here. And usually we call this artifact as noisy. So we can say that the image looks noisy for this higher position. Even though the images are noisy when the source is placed higher above the collimator using a source holder, the position of the source is still apparent in the image produced. As we can see here, it's still showing correct location of the source. These are the test cases I decided to do for the experiment. Cases 1, 2, and 4 have been shown in the previous slide, but I was curious to see the effect of some sort of a shielding on the reconstructed image. Therefore, I included a test case that has an aluminum alloy piece placed under the source. So that is represented here in the MCNP visual editor program by this red geometry. So, well, as expected, again, you would definitely see a much noisier image resulting from this arrangement. So this is how the experiment setup looks like. I have these 6 GM tubes placed in a radial arrangement on a cardboard. This allows me to slide them underneath the tank from this side and keep them all together in place. Each detector is connected to its own rate meter, which has a built-in timer. So I can just set the timer to 15 minutes and press count to start the measurement. The support structure here is not simulated in MCNP, as these are just placed to make sure that the collimator would stay in place. And these are some pictures that show the source positions. As mentioned before, measurements are taken 15 minutes each, and with another 15-minute background for each configuration. So these pictures were actually taken from the opposite side. So if you were to stand on this side facing this direction, you would see that this picture actually represents the lower right corner position, which is the case 4 position. You can see a small pump in the water, which is what I use to fill water into the pipes. And there's another bigger pump, which is not visible in any of these pictures, that I use to remove water from the pipes. So the source, as you can see, is placed in a pill bottle so that I won't get stressed out trying to extract the source if it ever falls into the water and sinks to the bottom of the tank. These are the source positions for case 2 and case 3. And this is the source holder that I was talking about that allows for the source to be placed farther away from the collimator. Again, the height of the source holder is about 11 inches. And the aluminum alloy piece under the cesium source can be seen here in this picture. In addition to the 4 test cases, I decided to test an unknown position as well. This is purely going to be measurements without simulations, just to see if the image reconstruction using the data from this unknown position would yield an accurate localization of the source. So experimental measurements are currently ongoing. So you would probably have to email me after about 6 months or 1 year, God knows when, if you're curious to know the final results from these measurements. To demonstrate the power of compressed sensing, here are images produced from different number of measurements with an increment of 10 measurements from the previous one. So it can be seen here for case 1, it could take as low as 30 measurements to get an image that shows the correct location of the source. And for case 2, it could take as low as 50 measurements. Case 3, it's the same thing, 50 measurements. And finally, for case 4, it could take as low as 20 measurements. However, it is important to note that simulations and real life are 2 totally different worlds. It could always be rainbows, sunshine, and unicorns in the simulation world. But I definitely expect that the images produced using experimental counts would need higher number of measurements. And so we'll see how it goes. As I've mentioned before, the experiment is still ongoing, and there have been a lot of challenges in completing the experiment, and especially during this unprecedented COVID time. To conclude, this presentation has demonstrated that the proposed proof of concept design was promising for a gamma source with a simple geometry through MCMP simulations. And I'd like to end this presentation with a final note that this research is important because it has provided theoretical evidence that the proposed design concept works. The non-negative least square method is shown to be successful and useful if the measurement process and data have inherent compressed sensing properties. The simulation model presented, if verified with experimental measurements, can serve as a useful baseline design to model a more sophisticated design. And finally, research on simulations of compressed sensing application in nuclear security, backed up by experimental result, is completely new. So I hope that this work will contribute to the advancement of research in the field. So that is all I have for today. Please accept my apology for not being able to join you in the live session. Feel free to scan the QR code shown on the slide, which will bring you to a form where you can let me know any questions, comments, or just to say hi if you'd like. I'll get back to you as soon as I can through email. Thank you very much. Terima kasih, and jumpa lagi, y'all.
Okay. Thank you, Linda. So it was a very, very enlightening talk on the application of compressor. On the application of gamma source imaging for nuclear security using non-least squares. So, I would like to invite all the participants with me to give a clap to Linda for her very enlightening presentation. So we will break for a few minutes. I would transfer this session to our committee members for the next event. Thank you. Bye. See you.
Welcome back to Nuclear Science, Technology and Engineering Conference 2020, iNuSTEC 2020. My name is Sofwan bin Shalbi. I'm a chairman for this session. I'm a student for PhD in nuclear engineering. So for this session, session 5A, titled Environmental and Safety, will be held from 10:10 to 12:30. So before we start our presentation, my first presenter, I would like to remind to all the viewers from our YouTube live, please like, subscribe, and share the link. And if you have anything or question to us, feel free to chat on our live chat. So, without further ado, I invite Ms. Nur Shuhada Matbai for the first presentation. Thank you.
Thank you, Chairperson. Assalamualaikum and good morning. Today I'm going to share my presentation titled The Elemental Distribution Study of Heavy Metals, Iron, Copper, Cadmium, Arsenic, Chromium, Nickel and Mercury in fish species at local market Muar Johor using SEM-IDEC. Next slide please. Here is the outline for my presentation today. I'm going to talk about introduction, objective, method, result and discussion. Next. Heavy metals pollution is a major concern worldwide due to the toxicity, persistent nature, non-biodegradable and its accumulative behavior. It is caused by industrialization, urbanization, agriculture and other human activities. Heavy metals from this activity will discharge into the sea or rivers, accumulate in water, sediments and aquatic food chain resulting in sublethal effects or death in fish population. Heavy metals enter the aquatic food chain through the direct consumption of water and food or through the muscle or gills. Next slide please. Fish are at the top of the aquatic food chain and considered as one of the bioindicators of pollution. Besides that, fish are the major source of protein to human. Thus, the human body is easily receive the heavy metals concentration due to the fish. Therefore, the analysis of the heavy metal in fish will reflect the level on sediment and water of the aquatic environment. Next slide, please. Next, fish have the ability to hold toxic materials in a small concentration to high concentration in their body without harming them. But the toxicity will affect the humans who feed on them. A small amount of heavy metal can be held either for a short time or permanently in their body. Thus, fish in the polluted water will accumulate high concentration of heavy metals along the time. For example, a high concentration of mercury, arsenic and cadmium could be harmful to the living cells and prolong the exposure to the body caused by illness or even death. For example, a cadmium exposure produces the kidney damage and hypertension, while arsenic exposure can cause cancer and abdominal pain. Chromium can cause lung damage and cancer, while nickel can cause damage to the lung, liver and kidney. Mercury is highly carcinogenic and cause joint disease and ailments of the kidney, circulatory system and nervous system. Next slide please. The distribution of heavy metal in fish differs due to the habitat and feeding habits. The information on the distribution of heavy metal in fish resources from the local market in Malaysia is still lack. Therefore, this study aims to determine the amount of heavy metals at the atomic percentage level in fish sample using rapid and analysis technique, which is SEM-IDEC. Next, in order to achieve the objective, there are several methods that will be done to achieve this objective. Next, the Sample collection process is performed in the wet markets at Bukit Gambir. The sample collected are Selawadas leptolysis, which is known as Sela, Rastelija canaguta, known as Kembon, Megalaspis cordila, Cencawu, Disapterus huxley, known as Layan, and Eutinus affinis, which is known as Tongkol. The table below shows the land that is recorded for each fish sample collected. Next slide. The fish sample that will be collected are washed using distilled water to remove the skin surface depth. Then the fish sample will be cut into pieces to reduce the drying time. The head, viscera, and gills were cut. Then the sample are freeze-dried for 48 hours to remove moisture content. The dried samples are grinded into 100 micron of powder form. Next slide. Next, please. The powder sample then is mounted on the stub with the conductive carbon tape. Previous slide. The powder sample is mounted on stub with the conductive carbon tape. Then the sample is powder coated with gold to avoid charging during the analysis. The imaging capability of the microscope is used to identify the specimen of interest. The percentage of samples are analyzed by tree scanning. 3 fine spots area are selected and the determination of elemental percentage is based on average scanning. Next slide. For the morphology structure obtained for all fish samples can be shown in figure. From this morphology analysis, it is clearly seen that the particle size for all types of fish species was different and the distribution of each particle is uneven. The morphology structure for Selawadas leptolysis exhibits smoother surface compared to other, while Disapterus huxley and Eutinus affinis have a similar particle size. Next slide. The quantitative analysis of heavy metals was given in atomic percentage. The result shows that the level of cadmium, mercury, arsenic, copper, iron, nickel, and chromium are varied according to the samples. The concentration of cadmium, mercury, arsenic, copper, iron, nickel, and chromium were classified according to different fish species. The same applies to the study done by the previous researcher where the heavy metal distribution were varied among different fish species due to the metabolism and the feeding patterns of the fish. The mean concentration of the heavy metal found in fish species was 0.173 for copper, 0.022 for iron, 0.02 for mercury, 0.016 for nickel, 0.015 for arsenic, 0.014 chromium, and 0.0 for cadmium. From the observation, it can be seen that the trends for the concentration of heavy metals for all fish samples were in descending order, which are copper, iron, mercury, nickel, arsenic, chromium, and cadmium. Next slide. Rastelija canaguta was found to have greater atomic percentage concentration of heavy metal as compared to the other fish species. Most of the heavy metals detected in our canaguta is mainly consists of cadmium, arsenic, chromium, copper, iron, and nickel with atomic percentage concentration of 0.01%, 0.02, 0.03, 0.22, and 0.04% respectively. Additionally, the figure shows that copper was found to be the highest concentration than the other heavy metals. The distribution of heavy metals in descending order for Rastelija canaguta was copper, iron, chromium, arsenic, nickel, and cadmium. This trend was similar to the outcome obtained from the previous study where copper was detected to be the highest among the heavy metals. The finding obtained from Rastelija canaguta suggests that the cause of high copper reading is due to the high copper concentration in the fish catching area environment. opinion is supported by the other study where copper is the highest detected in fish due to the fish species taken from waters enriched in this element. It was proposed that copper is important in all organisms in a trace amount, and it serves as a constituent of respiratory enzyme complex in the human body. And due to its role in facilitating iron uptake, deficiency of copper can cause the impairment of chromium-like symptom qualities and vulnerable to infections. Meanwhile, cadmium, arsenic, chromium, iron and nickel were detected in cell-iodized electrolysis with a percentage concentration of 0.01, 0.29 and 0.02. It shows that copper and nickel were found at higher percentage concentration than the other heavy metals. The level of accumulation of heavy metals in cell-iodized electrolysis in descending order was copper, nickel, cadmium, arsenic, chromium and iron. In present study, arsenic and cadmium were only detected in Rasteligia carnacuta and cell-iodized electrolysis. The existence of the arsenic in this particular fish may result in poisoning to consumer as reported by the National Environmental Protection Agency. Next slide please. The heavy metals compound found in Megalaspis cordilla is mainly consists of chromium, iron and nickel with a percentage concentration of 0.01, 0.02 and 0.02% respectively. The general observed trend for the metals for Megalaspis cordilla was iron, nickel and chromium. The lowest percentage concentration of chromium was recorded, while iron and nickel showed the same percentage concentration, which is 0.02%. As for the Disapterus huxley, the heavy metals concentration observed were mercury, chromium, iron and nickel with a percentage concentration of 0.02, 0.01, 0.02 and 0.01 respectively. The trends for the metal for the Disapterus huxley in descending order was mercury, iron, chromium and nickel. The result shows that mercury and iron recorded the same concentration that can be seen in the figure. Cadmium, arsenic and copper were not detected in Disapterus huxley. Mercury is highly carcinogenic and produces adverse effects during developmental stage as a result of acute and chronic exposure. In present study, mercury had only been detected in Disapterus huxley. Next slide. The detected heavy metals in Eutinus affinis were chromium, copper, iron and nickel with percentage concentration of 0.01, 0.02 and 0.01. The heavy metals in Eutinus affinis follow an order of iron, chromium, copper and nickel. In Eutinus affinis, iron was the highest concentration of heavy metals detected with 0.02%, while chromium and copper and nickel record the same concentration, which is 0.01%. The study done by Ahmad and Bad in 2015 found a similar finding, where ferrin being the highest concentration found in fish. In the current analysis, chromium was found at low levels in all fish samples close to those examined in Turkey and Malacca. Next slide. From this work, it can be concluded that the atomic percentage concentration of cadmium, arsenic, chromium, iron in Rasteligia carnacuta was found to be the highest compared to the other fish species, while copper was the highest in cell-iodized electrolysis. On the other hand, some amount of mercury was found in Disapterus huxley, while chromium, iron and nickel are mainly observed in all fish samples. as overall it was found that most of the heavy metals elements in Vastalija Kanaguta is found, while Megalaspis cordilla contribute the lowest heavy metals concentration. As Vastalija Kanaguta has the highest heavy metal content, hence it could give a risk of disease to human beings. However, the amount of heavy metals that accumulate in this particular fish can be considered very low concentration and still safe to be consumed. Next slide. This study was funded by the Postgraduate Research Grant DPPS UT Hasham. Next slide. This is several reference that I use in my study. Next. And that's all. Thank you.
Thank you, Madam Nur Shohada, for the great presentation. So, we move to next presenter, the Big Data Analytics Nuclear Security Framework by Ms. Maizura Ibrahim. Please welcome.
Thank you, Mr. Chairman. Assalamualaikum and good morning to the iNuSTEC 2020 participants. I would like to share a bit of the output of our research project entitled Big Data Analytics Nuclear Security Framework. Next. Okay, this is the project team leaders. This is the project team members, which is I'm the leaders, and we are 10 researchers from 10 research officers from IT centers, Nuclear Malaysia at Kajang, Malaysia. Next. All right. So this is the content of this presentation. It would be the first introduction. I will introduce about the background, nuclear security definition, big data definition, and what is big data analytics actually. And then the second part will be related, my related works. It will illustrate anchor paper gap found in the literature, and then the fundamental basis of the framework. And the third section will be the proposed framework, and the last section will be conclusion and future works. All right. Then next slide. This is basically the introduction of the project. As we all know, information technology is a key driver for the development strategy and progress in many areas. And one of the area is the nuclear security area. And then with the evolvement of big data analytic technology, it's initiate innovative changes in the strategy for nuclear security. And with these changes, it provides solution of a problem facing by most of nuclear organization in the world, which is a silo data management practice. And then this silo data management practice actually causes a suboptimal nuclear security system. Okay, this is the problem segment for this project actually, which is based on the articles published by WINS, the World Institute of Nuclear Security, in 2015. So we move to the next slides, please. Okay, this is actually the nuclear security definition. Okay, here we can say that nuclear security is the prevention, detection of, and response to theft, sabotage, unauthorized access, illegal transfer, or any others malicious acts that involve nuclear material, other radioactive material substances, their associated facilities, and then their associated activities. So this is the definition made by the IEA in NS Nuclear Security Series in 2008, which widely used in the published articles in journals and conference. So next slide, please. We come to the definition of big data. So before we go to big data analytics, we have to know what is big data. Big data is actually a data with a specific criteria. This criteria, which I take here is data with high 4Vs. 4Vs mean high volume, high velocity, high variety, and high veracity. So these 4Vs of data require new form of processing. Why we want to process them? Because we want to enable enhance decision making, insight discovery, and process optimization. This is actually the definition which is based on the article published by Gartner in 2012. But currently, these 4Vs of big data is currently up to 10Vs actually. So as you can see on the slide, currently it is up to 4Vs. They have added about 6Vs from the base 4Vs. Okay. Then we move to the next slide. All right. We have known about big data. And then now we come to the definition of what is big data analytics. First, we have to understand that analytics is the process of the big data using CPU, GPU, and artificial intelligence algorithms to detect patterns and generate predictive signals for prediction, decision, and solution making. And then when we combine analytics and big data, it's become big data analytics. So what is actually big data analytics? Big data analytics is about processing the big data by creating or applying artificial intelligence methods such as machine learning, deep learning models, or other AI methods such as knowledge-based method or others. Why we want to process? Why we want to do big data analytics? Actually, we want to find new insight and patterns that are useful for enhanced, optimized decision making and prediction. Next. So we come to the related works. All right. This is the works that is related to this project. First, firstly, this project is related to the two reports published by WINS in 2015, which is the anchor papers of this project. And then this is also the progression report of our unpublished works that have been started from 2017. And then from our literature review, there exist several initiatives in applying big data analytics in the nuclear sector. For example, WHO have adopting big data for an integrated disaster management systems comprised of flood management and nuclear disaster management. And we also found three research that apply big data analytics for the operations and maintenance of nuclear power plant. It is from South Korea and USA, and if I'm not mistaken, from Japan. And then we also found that ROE 2017 adopting big data analytic approach, and this research specifically using sentiment analysis of social media to get an insight into the public acceptance of nuclear power in South Korea. But from the literature view, we have yet to find evidence that there exists research in big data analytics specifically for nuclear security. So there is a gap in this research, in the research in applying big data analytics for nuclear security. So we actually, it is our vision to propose this framework to fill the gap. So next. So here, we enter to the proposed framework section. That's an important highlights where we want to note here. The first is the context of this framework. Okay, this framework is developed from a data management point of view. It illustrated how data from the nuclear security system should be managed, integrated, so that we want to achieve real-time and autonomous analysis. Why we want to do real-time and autonomous analysis? Because we want to carry we want to improve or optimize the required situational awareness. This is the problem statement that was published by WINS in 2015. So here, this framework also, we imply integrated data analytic approach. It is an approach in managing organizations that are led from top, where all information and data are used to generate value and support to achieve the successful of organization management, maybe. And then from the security point of view, so this framework imply that security must be viewed and operated as an enterprise-wide activity and fully integrated with other business process and objective using enterprise-wide system or software. So for the purpose of autonomous analytics, it is highly important that the related data from nuclear facilities or operator are fed in real time into the state level data management system. So next slide. All right. So this is the first level framework. So actually, this framework is come into two levels, which is the first level is for nuclear facilities and operators, and the second level is for state level. So we want to be able to propose this because we see in wide point of view that this security of nuclear security could be managed, integrated, and widely across state. Okay, so we come to the first level of the framework. So firstly, we name this framework is the Integrated and Intelligent Nuclear Security, which is the I2NS. You can see the logo in this slide. So in order to realize the big data analytics for nuclear security at the state level, the security system that falls into the regime of nuclear security at facilities or operators needed to be fully digitalized. First, we have to digitalize the nuclear security system at nuclear facilities level. So all manual systems should be upgraded into computerized base so that the related records and files could be stored electronically in a digitalized form utilizing existing database technology as depicted in the lowest level of this framework. So there are 4 components that are critically important for digitalization from our point of view. It is the physical security, nuclear radioactive material accounting and control, personal trustworthiness evaluation, and data visualization. Okay, as you can see here, physical security, nuclear radioactive material accounting and control, and personal trustworthiness evaluation is the component that based on the international legal security framework published by the IEA, and the fourth components, which is the data visualization, is from the big data analytics component. Apart from that, all of these components are linked to integrated online alert system, so that we could trigger the alert system from each component whenever radiological crime scene management occurred. Okay, for each of the component, the related backend database must be also integrated to form a data pond or data lakes, depending on the needed storage capacity for the respective facility or operators. Okay, next slide, please. So this is the back end database architecture for facilities level. So we use Hadoop framework, we propose Hadoop framework for the integration of the related databases, and we have identified the type of data which consists of unstructured data, semi-structured data, structured database, and also media socials application. So the recommended database architecture consists of the respective data from component of physical security, personal security, and NMAC system, and we recommend Hadoop framework for this because instead of relying on the expensive and different system to store or process the data, Hadoop is an open source free software that enables distributed parallel processing of huge amount of data across inexpensive software. All right. And it is also important to state here that because the data could be used from the data lake or data pond warehouse, the data need to be cleaned to ensure the correctness of the data and maintain the highly integrity level of the data. And then the data also must be explored, and then to develop the analysis model that could be lead to the development of data visualization and analytic products that usually display as a dashboard system. Okay, and as you can see from this slide also, we use the trustworthiness profile for personal trustworthiness evaluation. We imply sentiment analysis of the social media to evaluate the trustworthiness of the personnels, and this output will be integrated into the personnel profile at the enterprise database. All right. Then we move to the state level framework. Next slide, please. Okay. This is the state level framework proposed by us. Okay. So the element in the framework are designed based on the nuclear security elements stated in the International Legal Nuclear Security Framework and the need to perform autonomous analysis of the data for the realization of the enhancement situational awareness. So as you can see in the framework, we have external data from nuclear facility and operators, and then we have internal data from regulatory bodies, and also the external data from government GIS or GPS data provider. And this data will be fed into the we can say the big data analytics system for the data acquisition and expression. Okay, during the data acquisition process, we will process the structured data, unstructured data, and semi-structured data, and then we will do some data cleansings to correct the data and to maintain the integrity of data, and then we will do the data expression. And we have also identified from the types of data that need to be fed from nuclear facility, the types of data that could be obtained from the regulatory bodies, and the types of the data that could be obtained from GPS or GIS data provider. And all of these data will be used to develop an analysis models so that we could develop a data product where the data product will be consists of the analytics and visualizations. So at this level, we identify some outputs that could be from the developed data. And then the first output is the improvement of the X related to the nuclear energy or atomic energy. And then improvement of the nuclear safety related X, and then improvement of the state level nuclear security implementation and compliance. And today the output could be viewed from the data dissemination module, which mobile phone, tablets, and PC, and beneficial to the stakeholder, which we identify as regulatory officers, enforcement officers, protection officers, national disaster management agencies, police officers, and the IAEA itself maybe, and then publics, of course. Okay. So we come to the next slide, please. Okay, we come to the conclusions and future works. Okay, here we have presented a conceptual big data analytics framework for nuclear security that is proposed in the context of data management point of view. So the framework consists of two levels. First level dedicated to the implementation of nuclear facilities and operators, and the second level is for state levels implementation. And we have yet to evaluate this framework actually. And then for future works, we want to proceed with evaluation applying empirical methodology. So currently we are in the process of developing survey questionnaires, and we have reviewed a number of methods to evaluate this framework, and we have choose rush measurement model for the evaluation process. So this is our feature works. So with that, I thank you for the attention. Okay, here I would like to acknowledge the IAEA for providing the funding for this project. It is from the CRPJ 2011, improving the security of radioactive material throughout its life cycle, associated facilities and associated activities. And I will also want to make acknowledgement for Malaysian Nuclear Agency and universities that join in this project. So here is the references. Yes, and thank you.
Okay. Thank you, Ms. Maizura Ibrahim, regarding for the presentation of a big data analytic nuclear security framework. Very good information and research. So we proceed to the next presenter. The floor is yours. Please welcome Ms. Suzilawati Muhammad Sarawi. Thank you.
Let's clear the line.
Okay, Suzy.
Okay, Assalamualaikum and very good morning. Thank you to Mr. Chairman and all the participants in the iNuSTEC 2020. My name is Suzilawati Muhammad Sarawi. I'm from Malaysian Nuclear Agency, and this is my team to produce this paper, Dr. Zalina, Ms. Azima, and also Dr. Kamaluddin Samudin from Malaysian Nuclear Agency as well. And the title of my presentation today is Laboratory Facilities for Nuclear Forensics Investigation in Malaysian Nuclear Agency. Next slide. This is my abstract for this paper, and you can see this paper will discuss the capability of laboratories in the Malaysian Nuclear Agency and the internal arrangement in handling nuclear forensics analysis. And the keywords for this work is the nuclear forensics, which is, I think, you already heard very much from the presenter previously, Madam Maizura. Then we do have nuclear security and also the laboratories. We have many laboratories in Malaysian Nuclear Agency, but we will choose some laboratories which is really needed to be used as nuclear forensics laboratories. Next. I'll straight away to the introduction. Before I go further, I would like to let you all know what nuclear forensics is. So the nuclear forensics is defined by International Atomic Energy Agency as examination of nuclear or other radioactive materials or of evidence contaminated with radionuclides in the context of international or national law or nuclear security. This is what Madam Maizura talked about before, which is the nuclear security aims at the prevention and detections, all about the unauthorized access, illegal transfer, or other malicious acts involving nuclear material. And that's why we need, if you can see, all over the world, in the internal border, international border, you will see many of the detection instruments to detect and to monitor wherever the moving or the transfer of nuclear material or radioactive sources come in or out from each country. And if you can see also in Nuclear Malaysia, we do have a radiation portal monitor in the entrance purposely to serve as nuclear security aspect. Next, please. So nuclear forensics actually is a subset of the nuclear forensic science, so we cannot separate them. The nuclear forensic is a multidisciplinary field and integrated of many fields such as geology, radioanalytical chemistry, physics, material science, and etc. Then, how nuclear forensics supports a criminal prosecution, you can see in the slides. Okay, once you have to detect the nuclear or radioactive materials, for example, in the border, during the transportation and so on, and then the regulatory body will take the sample, the evidence, and they will send to the lab to analyze, and they will have to integration using a comprehensive database. I believe we can use Ms. Mazura work on this, and then you have to link all the things, the people, the technology, and then we can have some finding and then go to the prosecution in the courts. And what we can answer when you are using the nuclear forensic analysis, okay, during the nuclear forensic analysis, actually we are doing the characterization, interpretation, and also the reconstructions. From the nuclear forensics analysis, because of nuclear forensics, because of nuclear material and radioactive sources have a very unique identification, such questions can be answered. What is the material? So we do know many of sources, uranium, plutonium, cobalt, and so on. So we have to identify what is this, okay? And then we can know the country of origin where the material was produced, because in this industry, there are several countries have a role in the production of nuclear material legally. So we can know which country produced this kind of process. Next, from the analysis, we can estimate the date of production. Most important, we can know what is the sources intended use, whether is it for military, for agriculture, or for medical, and so on. For your all information, until December 2014, there are 2,656 cases of nuclear forensic incidents was reported in the Incidents and Trafficking Database, which is controlled by the International Atomic Energy Agency. Hence, it's very important for each country to have nuclear library in order to be used in nuclear forensics. This library can be used for comparison globally. So, next slide, please. So, as you know, this is for your information. Nuclear Malaysia is the promoting agency in using of nuclear technology in various fields in the country. So we do have, we is the biggest licensee in Malaysia. We do have radioactive sources, we have apparatus, facilities, and so on. And under National Security Council, the Nuclear Malaysia is a technical support organization in the radiological and nuclear emergency events. So we do receive an explanation in 2016 in establishing and developing nuclear forensics capabilities. And finally, we understand that this field is an integration and involvement of several divisions in Nuclear Malaysia, which I will talk more detail later in my presentation. Next slide. Next, please. So this is the objective of this work. We are actually developing SOPs amongst the library, amongst the laboratories in Nuclear Malaysia. So first objective is to assist in the investigation of criminal events and emergency involving radioactive or nuclear materials. For Example, in our border, if we found illegal transportation of nuclear material or sources, so we need to make an analysis on the sources and make a report, produce a report to the designated authorities. Second objective is to serve as a reference and guidelines for nuclear forensics analysis in nuclear measure, and also serve as a national services. And the third one is to ensure the effective and efficient use of the laboratory facilities in handling the nuclear forensics investigation. So we try to fulfill these three objectives during this work. Next, please. This is the methodologies that we already done several years back. Okay, if I'm not mistaken, we started in 2013. So we already mapped what training we need for all our staff, and until now, 10 staff undergone training abroad in Hungary, Korea, Germany, and so on, in various fields in the nuclear forensics aspects, such as crime scene management, handling the evidence in the lab, analysis the evidence in the lab, and also how to make a report to the designated authorities. And in 2016, as I mentioned earlier, we already request an expert mission to identify our strengths, capabilities, and expertise. So from the missions, the finding is promising that we can establish a nuclear forensic in nuclear measure. So then we conduct internal courses, several meetings, discussion workshops among our staff to integrate all the people and also the laboratories in nuclear measure. Next. Next. So this is the action model which is suggested by the expert and adopted from the IEA guideline. So from the police officer, they will send straight away all the evidence or sample from the crime scenes from the crime scene to the lab. Okay. Then we will in the lab they will make a categorization. So you have to categorize whether this is radioactive sources or nuclear material, and then you have to make a characterization in terms of radiochemistry, the purity, and so on, analytical chemistry, and also the material technology. So you have to characterize whether this is the what is the composition and so on. And we also have to perform also the traditional forensics. Okay, you have to find DNA, match the DNA if needed, and of course fingerprints, so you can know who are bringing this kind of radioactive sources or nuclear material in the country. Next. So this is what actually we already developed, but still in the draft. We are waiting for approval from the management. And this charge we could say this will be used if the nuclear analysis cases in I believe we can use this charge, but we have to test it more frequent, better understanding. I will to discuss more on the another slide. Next, please. Next, please. So this is the results. We already identified 5 divisions to be involved in the nuclear forensics in the agency, and each lab will have their own tasks. So you can see here we have a radiation safety and health division, we have a waste and environmental technology division, industrial technology division, and also waste and also industrial divisions. And this rector group is from the technical support division. Is very important in operating the analytical chemistry lab which is in the number 2. Okay. I will try to discuss a little bit on the task for each divisions. Health physics group under the radiation safety and health division, we are the divisions who communicate to the regulatory body because we have a radiation protection officer in this divisions. So these divisions find as a secretariat, which is they will receive the evidence and then they will conduct the preliminary examination of the evidence in terms of radiation safety, how much the doses, is it really dangerous or not? Do we need to another etc. PPEs in handling and so on and so on. And then we will distribute the sample among the labs. And bear in mind, maybe not all labs listed here will perform the analysis because it depends on the cases and it also depends on the authority needs. Okay, and then this division, the secretariat, will make a report and will communicate to the designated radio analytical measurement and also the chemical analysis. So we can know the impurity and purity of the sources. Okay, whether we have another element in the sample and so on. And then the material technology group will make the characterizations analysis using X-ray machine and so on, just to ensure another further analysis. And more advanced analysis will be done using the transmission electron microscope if it's needed. Okay, next please. Next please. So this is some of the equipment that we have in the lab. As I said just now, we have to identify the evidence. So using the identity finder, you can know what is the sources, what is the radioactive material. But you still need a further analysis to determine the mother, daughter, and the purity and so on. Then we do have a gamma spectrometer lab, which is accredited by, with ISO 17025. And this gamma spectrometer lab actually is the only lab approved by the Ministry of Health Malaysia to conduct radioactivity contamination tests on the imported food in case of a nuclear emergency, such as during the Fukushima Daiichi nuclear accident in March 2011. We collect a marine sample from our sea and perform a measurement. And we also analyze our environment sample, such as grass, seawater, to ensure our environment are clean and not deposited with any radioactive sources from Japan that time. And this lab actually worked many years before this. Okay, and they also analyze food contain to ensure the heavy metal elements and radioactive sources in the food before go to the market. Okay, and during the nuclear forensics process, the laboratories will be identified by secretariat based on the requirement from the designated authority for further analysis, just like I said before. So it depends what is the authorities' needs. Maybe they just want to know about the sources. Maybe they just want to know people. So we have to do more analysis and deep analysis. Next, please. So as a conclusion, currently we have 10 standard operating procedures was compiled, and we are hoping this development could be used and serve as a reference and guidelines for nuclear forensic analysis, not only in nuclear Malaysia, but also to support nuclear security system in Malaysia. And I believe compilation and written document is very important tool to preserve the knowledge and skill. Of course, it's a part of knowledge management in the agency. So with that, I end up my presentation. Thank you. Thank you for your attention. Stay safe, everyone.
Thank you for the great presentation, Ms. Susilawati. It's a very good information because I know that Malaysia have their own nuclear forensic lab at the Malaysian Nuclear Agency. So before we proceed to our next presenter, I would like to keep remind and ask all the viewers and also participants to like, comment, and share this iNuSTEC 2020 for the first time in live. We do the conference on virtual teleconference. So without further ado, let's proceed to the next presenter. I would like to invite Ms. Noraisha for the presentation. Thank you. Please, welcome.
Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh, and very good morning. Thank you to Mr. Chairperson, and thank you to all the viewers as well. So I am Aisha Osman from Agency Nuclear Malaysia. So my team and I are doing this kind of radio tracer work, radio tracer technology in enhanced oil recovery projects. So we hope that this kind of intervention of radio tracer technology in the new enhanced oil recovery applications can assist the oil company in Malaysia in the near future. So please, next slide. Okay, the topic of my presentation today is the investigation of water flooding activity in vertical sand column using gallium-68 as radio tracer. As you know, radio tracer is the radioactive source, which is the material which emit radioactive in terms of alpha, beta, or gamma. So in this case, we are using the gamma type of to my slide. So I think maybe I should proceed with my presentation without the slides in front of me. Okay, I think I should continue with my presentations. So this work is about introducing this radioactive source into the oil reservoir in order to detect the movement or the water tracking inside the reservoir. So in this study, we are actually mimicking the oil reservoir so that the tracer that we injected can be mapped out. So these ideas will give the offshore offshore engineers to have the wide perceptions and knowledge on how to detect or look at the anomalies if there is any inside the reservoir in order to enhance the recovery. Hello? Okay, ladies and gentlemen, so we have a technical problem.
Slide tak keluar.
Slide tak keluar?
Tak nampak slide.
Bukan slide ni is being controlled by
Not yet.
Yeah. Not yet. Okay.
Okay. Live sekarang.
Okay, Assalamualaikum warahmatullahi wabarakatuh, and very good morning, and thank you to the Mr. Chairperson and all the viewers. And again, sorry for the technical problem that we faced recently. So again, I am Aisha Osman from Agency Nuclear Malaysia. So my team and I have conducted radio tracer technology for the intervention of this technology inside the reservoir. For that, we conducted preliminary work. So I will explain more details in my next slide. Next slide, please. Okay, the topic of my presentation today is the investigation of water flooding activity in vertical sand column using gallium-68 as radio tracer. So radio tracer is the substance which emits gamma. So as we know that there are many types of emitting tracer like alpha, beta, and gamma. But normally for industrial application, we use a gamma emitting tracer. But in this case, for this specific study, we use gallium-68. So this gallium-68 is the nuclear medicines, which is widely used in nuclear medicines. So this GA68 is emitting positron, the alpha, beta, or gamma. So it is being extracted, or it is eluted from the mother GAGE, germanium gallium-68, which is in this study, which is sponsored. We have to acknowledge the IKN for providing this generator so that we can conduct this kind of work. Okay, please. Next slide. Okay, this is the outline for my presentation today. So we start with the introductions, methodology, results and discussions, and conclusions. Next, please. So as for the introductions, so it is about 47. Malaysia has about 47 of reserve oil wells, which produce about 36.8% of oil. So it is stated in the 2003. So which means that we have about 63.2% of oil which is considered as residual oil. So this remaining about 60% of oil is trapped inside the rocks in the reservoir. So according to the previous author in Malaysia, it did mention that Malaysia will retain about 19 years of producing oil in Malaysia. Therefore, we have to really make full use of application of enhanced oil recovery to excavate or extract out the remaining 63.2% of oil in our reservoir. Therefore, in this study or for this presentation, we are showing the preliminary work that we introduced so that the petroleum company will acknowledge our work to be incorporated with their work in the future. Next slide, please. Next slide, please. Okay, this slide shows the stages of oil recovery. So it starts with the primary oil recovery, in which by conducting this primary recovery, it will recover up to 15% of oil reserve in the reservoir. So in this case, they use internal pressure that is existing naturally inside the reservoir or using the artificial lift. Thus, they are remaining about 85% of reserve oil in the reservoir. Therefore, the oil company is introducing another secondary oil recovery technique. This technique, which encompassed of water flooding or gas flooding to extract up to 40% of oil reserve inside the reservoir. So you can see here in the figure or in the diagram down there that the water is being injected continuously to the injection well. So this water flooding will give or will exert the continuous pressure so that the oil will be displaced and will be sucked out from the production well. So finally, the tertiary oil recovery, or we call it as the enhanced oil recovery. So for this technique, the oil reserve in the reservoir can be extracted up to 60%. So in this case, they use chemicals, or they use surfactants, or they use heat, they use thermal, or they use combustion technique in order to melt the oil in the reservoir. In the Middle East, the crude oil, which is trapped in the reservoir, is very viscous, so it's very thick. Therefore, they have to combust, or they have to introduce the continuous thermal. They have to burn the crude oil to make it melt so that it can be free-flowing and it can be transferred to the what we call the production well. Okay, next slide, please. Okay, as I mentioned earlier, so this is the stages of the oil recovery, not only in Malaysia, but all over the world. So at this stage, we are concentrating only on the secondary recovery, which is in the water flooding stage. Next slide, please. Okay, so what is water flooding and oil industry? So it is a secondary recovery in which water is injected continuously into the reservoir to displace residual oil. So this water will introduce high pressure, continuous pressure to extract out the trapped oil which is attached at the rock to the producing well. So the water from the injection wells physically sweeps the displaced oil adjacent to the production well. So it is mentioned here also that the water flooding technique is one of the most economically viable techniques for recovery of additional oil from mature fields. Next slide, please. So why we use radio tracer? So because we know that the amount of tracer that will be injected inside the reservoir is minute in size, which is so negligible in terms of the volume. It would be like up to 30 milliliter in volume. So it is a very, very incomparable or negligible in amount, but it is very high detections. Okay, so this radio tracer will be injected in the water flooding systems to penetrate, to permeate all through the water channels, all through the path lines that ever occur inside the reservoir. Because of what? Because most reservoir is, or most reservoir in Malaysia are anisotropic, in which that the property, the property is based on the directions or based on the locations. Okay, so the property of the materials is the property of the material during an isotropy in the real is constant. That's why it's very high in heterogeneity and very complex. Thus, we introduce radio tracer which can access and run across the reservoir, which contacts every portion of interest and giving information about the swab efficiency. Okay, so the fluid flow or hydrodynamics, we call it, inside the reservoir can be specifically described using analysis of residence time distribution models or RTD that will lead to ways in improving the oil recovery. So this tracer is not increasing the amount of oil that is trapped inside the reservoir. Instead, this radio tracer will give the behavior or will give the informations of the reservoir so that the offshore engineers can take actions on what is best so that the extraction of oil can be made optimized. Next slide, please. Next slide, please. Okay, this is the methods that we conducted for this study. So we use GA DOTA radioactive. Initially, we injected GA only. So as I mentioned earlier, GA is the positron emission type of radioactive. So we thought that by using this GA inside the using the water flooding, it's not so. We have to actually chelate the GA68 with the DOTA to ensure that this GA DOTA can represent the water flooding activities. Okay, so in this case, this GA initially was extracted from the parents or from the generator GA68, and after that, this GA68 should be mixed with HEPAs, or we call it as the abundance to prevent the rapid change of pH. And after that, we will add this solution with the DOTA. Prior to that, this DOTA should be heated at temperature of 95 degrees and at 10 minutes to ensure that we activate the chelating agent. So this DOTA and this GA will be mixed using the vortex mixer so that it will produce homogeneous mixer. Okay, so these are the parameters used in these experiments. And prior to that, in order to ensure that the GA-gelated DOTA that we produce is pure, we have to check using the TLC scanner in order to check the purity of the GA DOTA. And by using the TLC, we found out about only less than 1% of GA DOTA is not bonded well. So we produce about 99% of GA DOTA. So this DOTA is then used for our next experiment. So all these parameters have been set earlier in order to facilitate this work. So we have about 30 centimeter length of 5 centimeter perspective tube, which is arranged in a vertical And so this perspective is occupied by the about 150 micrometer size, the grain size of sand. And prior to that, we have to with the information water, and that we have to age our column with the oil. In this case, we use kerosene. So this kerosene or oil mimic the residual oil that I mentioned in the reservoir. Okay. So the water flooding activity commences when the action of continuously injecting the what we call the water flooding system from the syringe pipe. So this syringe pump is having about 0.5 gram per liter sodium chloride, or about 500 ppm saline. We call it as saline. So the volume is about 100 milliliter. So this 100 milliliter will be injected continuously inside this column, and at the same time the GA DOTA is also injected right after water flooding commenced. And prior starting this what we call the electronic setup, we have to install our sodium iodide detectors at respective locations. But the most important detectors or signals should be at the outlet, at the very outer part of the vertical column. So this column or this detector, this sensor, will provide you with the RTD, and this sodium iodide detector will be connected to the data acquisition systems, and we will track the movement of tracer using the laptop. Okay, next slide, please. Okay, so this is the TLC results to indicate the purity of the GA chelated with DOTA. So we found out that there is no other peaks observed, so that indicates that GA68 is very pure. And initially, the data that we gather or we observe, we obtain from the outer sensor is having this what we call having the parasitic signals. So these signals are not reliable. I mean, the signals should be eliminated. Therefore, we have to treat the data first before we conduct any analysis for RTD. Okay, next slide, please. Okay, so these are the what we call the models that we can observe or we can develop from the results at the outer part of the column. So there are perfect mixer in series model, perfect mixer in parallel model, axial dispersed plug flow model, and last but not least, axial dispersed with exchange model. So we can see very clearly that perfect mixer with parallel model fit the experimental model very well. So it also indicates that there is no obvious anomalies inside the plant. For example, the RTD curve here is at the center, and it is so symmetry, which indicates that it represents perfect mixers very well. And also, there is no indication of parallel lines or short-circuiting. And last but not least, we can not identify any what we call any dead zone or stagnant zones that are so common in the reservoir. Okay, so I will say that because of the preparation of a column is very good, it is well compacted. That's why the result is agree with the model. Okay, next slide, please. So why do we choose the perfect mixer model with parallel, perfect mixer with parallel model, because the calculation of SSE. So SSE is the calculation of error between the model and the experimental work. So these are all the parameters that represent each models. You can see here that the SSE value is the least, is the minimum when we choose the perfect mixer with parallel model. So when you compare with all models, so definitely we put the rank as 1. So when you see at the parameters of the parallel mixer with parallel model, so the top here indicates that the MRT, the mean residence time for this project, for this model is represented as 366 seconds. So this is the duration or the time taken the particles resides in the vertical column. So because it is represented by the parallel model, they have two paths. So the first path is tau 1, which is equivalent to 360 seconds, whereas another one is 295. The J value here representing the number of perfect mixes. So the J1 is 17 and the J2 is 3. So next slide, please. Okay, so this is the block diagram of perfect mixes in parallel model where we adopt from the IEA Tech Doc 2008. So as I mentioned earlier, because this experimental work is best represented by these perfect mixes with parallel models. So we have two parallel lines. So which means that this overall system of process is actually, or in a model, is being represented best with two parallel lines, two path lines. There are actually two path lines of the water flooding activity inside the column. So the Q is represented by the volumetric flow rate, and J is represented by number of perfect mixer. Okay, next slide, please. Finally, in the conclusions, so GA68 per se is a sand tracer and does not blend well with water fluid. So which means that GA can be considered as the sand tracer, in which the GA that we injected initially without chelating with a DOTA actually absorbed with the sand and not what we call dilute well with the water. So that's why this GA68 should be modified. That's why we introduced DOTA to represent the fluid flow. But the preparation is quite tedious. That's why we need collaboration from our team member, which is good in nuclear medicine, to prepare this GA68 DOTA. And based on the RTD model discussions, the sand column was prepared nicely because there was no indication of common process anomalies such as dead zone, channeling, and short circuiting. The perfect mixers in parallel model fits the experimental model due to the minimum value of SSE, sum of error, in comparison with other models. Next slide, please. I think this is my notes. Okay, so the acknowledgements go to the National Cancer Institute in Putrajaya for providing the GA68 generator, and also the acknowledgement should go to Prof. Jovan Teriska, our collaborator from the IEA, and also our collaborator from Norway, Prof. Torp Jonstad from IFE, Norway, and Dr. Quang from Canti, Vietnam. So while we are conducting this kind of work, we always conducting all these three experts so that we have the clear picture of what actually going on in the reservoir. Okay, not to forget all our plant assessment technology from Agency Nuclear Measure colleagues who participated in this experiment. We also like to acknowledge our funders, our sponsors from the IEA with research contract number, and 22898, and also from the KPT for the FRGS fund. With that, I end my presentation. Thank you.
Thank you, Ms. Noraisha, for the great information and also presentation. If you have any question to ask Ms. Noraisha, please feel free to ask in the live chat below. And don't forget to subscribe our YouTube channel. And for the next presentation, I would like to present my own research regarding to the study of mechanical and shielding properties of barat columenite concrete. Okay, proceed. Welcome back to our State 20. And today I would like to present a study on mechanical and shielding properties of barat columenite. So my name is Sami. I'm from UMP, currently doing my PhD on nuclear engineering. So next. So we start with the introduction. Next. So basically, when we talk about the research and we talk about the nuclear facility, we must know about the shielding because nuclear facility complement to the shielding. Without shielding, we cannot handle or operate the nuclear facility, and without nuclear facility also, we cannot have a shielding for the neutron. So both of them are complement to each other, and this study is aim to study the mechanical properties and shielding properties of barat columenite concrete for the BNCT research facility at the thermal column of our Trigger Mark II research reactor station. Next. For the literature review, what is a radiation shielding? So basically, when we know that shielding have the ionizing radiation have a four type of radiation, which include the alpha, beta, gamma, and neutron. And most probably and commonly used for the nuclear facility is lead and also concrete. But the concrete have their own disadvantage, and the lead also have their own disadvantage. For example, the concrete need the higher thickness to shield the neutron proton, and also lead advantage on thickness and also density. So basically, designing the shielding for neutron radiation is much greater in complexity than designing the shielding for gamma ray, because a part of a neutron, we have an unnecessary radiation also. And the purpose of using the neutron shielding material is to thermalize the first neutron and finally absorb them. And the shielding for BNCT facility include the beam stopper, beam shutter, and additional shielding. So basically, this research aims to design the shielding that can be used for our new BNCT facility. Next. So barat columenite as a radiation shielding for BNCT facility. As we know, concrete is known as the conventional material for radiation shielding. Its most basic form is a mixture of Portland cement, sand, coarse aggregate, and water. However, concrete can be concerned during its dismantle, since its element can be active due to the intersection with thermal and intermediate energy neutron. Concrete is also heavy and sometimes requires a large volume to shield against gamma ray and neutron. Next. I bet I can't see the slide because too small. So basically this table talk about the literature review about other researchers who use a barite and also columenite in their research to see the properties of mechanical and also shielding of barite columenite. And some of the researchers, for example, Otto use barite and get very good mechanical properties and also shielding properties. But some of the researchers, such as Mashibi, use both barite columenite as a main aggregate for their research. But unfortunately, the result is not good in terms of mechanical properties. So that's why my research focus on mechanical and shielding to get and meet the standard requirement for the shielding in nuclear facilities. So next. Then we proceed to the methodology next. So for the experimental work, we start with design the barite columenite concrete. We use the DOE or design method to design the mixture of concrete and get the formulation to design our barite columenite concrete. And then based on the design, we will do the test cube and the test cube will undergoing the curing process before the testing for radiation shielding and mechanical testing. So the test cube the size of test cube is 15 cm times 50 cm. So next, we go first for the shielding properties. So to evaluate the shielding properties, firstly we go to the gamma transmission test. This test will be done to find out the radiation shielding properties of barite columenite concrete on gamma. We use the cobalt 60, and this test is to see and evaluate the radiation shielding capability of the tube-scape test cube of barite columenite. Next. So the next shielding properties we investigate is neutron shielding properties of the barite columenite. So to conduct it, we use sand at the nuclear research reactor, small angle neutron scattering. So the test will be done to find out the radiation shielding properties of barite columenite towards the neutron, and the source is about 1 to the power of 5 neutron centimeter. And the test to determine the radiation shielding capability of test cube, you can see that from the figure 3 is we designed the experiment and we conducted the experiment of neutron scattering test. Okay, next. So we proceed to the mechanical properties. Okay, for the mechanical properties, we divide into 3 sections. And the first of all, we do the slump test. The slump test took place after the mixing of the concrete, and we already pour the cement, barite, and columenite, and so on. And before we put it into the test cube, we do the slump test first. Is to ensure the correct amount of water has been added to the mix. As we want to achieve the grade 40, we need to have a great workability of slump test. And the test was carried out following the ASTM C143. So this slump test is a function to determine the consistency of pressed concrete. So whenever we want to build up the new concrete or research on the concrete, we need to do the slump test. Next. Yeah, the next test is we use a ultrasonic pulse velocity test. So ultrasonic pulse velocity test is a in situ NDT method to evaluate the durability of the concrete. The evaluation was carried out based on the correlation between time of propagation or velocity log magnitude ultrasonic wave in the concrete. So from the table 2, we can see the guideline for catalyzing the quality of concrete structure in terms of ultrasonic pulse velocity. So to get the very good or at least good of concrete quality, we need to get 3.5 and higher. Okay, next. So the next and the last test we use for the mechanical test is compressive strength test. The compressive strength test was important to determine whether the concrete mixture meet the target strength or not. So after 20x day of the concrete being curing inside the water tank, then we took out and do the test on the concrete on the machine to see the strength limit of the concrete itself. So from this test, we can know which grade of the test cube we get. So the compressive strength test was conducted on the hardened concrete sample as prescribed by ASTM. Okay, next. So for result and then discussion. Next. Okay. So table 3 show that the mixture percentage of barite columnite concrete sample. So we have a main material for this research, and to do the barite columnite concrete, we have a cement, water, sand, columnite, barite, and plasticizer. So basically, we designed 5 different formulations of barite columnite, and each design was calculated based on the OE, and some of the design we substitute the columnite with the water, because normally in other research they use columnite as a band aggregate, but in this case we know that the columnite has boron, and boron very reactive with the water, so they react on the water and make the mechanical properties become lower. So that's why instead of make the columnite as a band aggregate, we substitute with the water. Okay, next. So this is the effect of barite and columnite in mixed concrete of neutron. So based on the table 4, we get the average data of Newton scattered percentage by barite columnite sample. So based on the sample, 5 sample A, B, C, D, E, we can conclude that the sample E have a very high Newton scattered, which absorb about 98%. And you can see from the figure, the E was the greater on neutron absorption compared to the other sample, and C get the lowest. Next. For the gamma reaction for barite and columnite concrete, we can see the table 5. Each of them have an average number and similar percentage of gamma absorption. But we can see from the table and data given, the sample D got highest of gamma absorption compared to others, but have a little bit different with the sample E, about 0.03. And you can see from the figure the percentage of the gamma absorption by all the samples. So basically, I want to say the sample is we do the 5 test cube for each sample. So this is the average data of each sample. Okay, next, proceed. So this is a mechanical properties. So basically, in table 6, show the mechanical properties testing result of Barat Columnite sample. We have sample A, B, C, D, E. After we done the shading properties, then we do the mechanical properties test for each sample. So for the slump test, the higher the slump test is means the workability of the concrete is not good enough, and it's not good to get the grade higher. For example, we can see from the sample A, the slump test is 75, but the compressive strength test is 0 because the concrete already crushed when we start to do the test, so we can't get the numbers and data for it. So from the slump test, we see that the B and E show the very workability for the Barat Columnite. And in terms of pulse velocity, we can see that most of the sample get 3.5, and only one, which is a sample A, get less than 3.5, which means all the sample, excluding A, got the very good quality of concrete. And the last one is compressive strength test. From this data, we get the sample B is a grade 33, sample C grade 32, sample D 32, and also sample E 42. So basically, from this table, we know that the sample E get the highest mechanical strength and also mechanical properties because achieve our target to get the at least grade 40 for our BNCT shielding. Okay, next. So as a conclusion, we know that the Barat Columnite can achieve a good quality if we design the experiment with suitable equipment and suitable testing. And from my research, we say that the Barat Columnite from my data get higher and also achieve the objective and get more than grade 40 and suitable for BNCT shielding facilities. Next. Reference, next. This is my list of reference. Next. Thank you. That's all for today for me. Welcome back to our conference. And we have a question from the live chat from Alarat LTD. The question is, where to source the barite? This material can be sourced in Malaysia. Okay, to answer this question, basically, barite and colemanite already have in our Malaysian Nuclear Agency, so I use it to utilize the material that already have in Malaysian Nuclear Agency. Basically, both barite and colemanite we import from Indian and also Turkey. So I hope it will answer your question. So without further ado, let's proceed to our next presentation. I would like to invite Ms. Nurul Huda. The floor is yours, please.
Okay, thank you, Mr. Chairman. Assalamualaikum warahmatullahi wabarakatuh. To all presenter and viewers. Okay, I'm Nurul Huda binti Mudri, Research Officer from Malaysian Nuclear Agency. Currently, I pursue my study for my PhD at University Putra Malaysia. So basically, this project is a collaboration project between Malaysian Nuclear Agency and University Putra Malaysia. So the title of my research is Synthesis and Characterization of Jatropha Oil-Based Polyurethane Acrylate for UV curing coating application. Okay, next. Okay, this is the outline of my presentation. Firstly, I will introduce the background of the study, followed by the methodology that we use in the study, and then result and discussion, conclusion, and finally the reference. Okay, as you can see on the right side, this is the process how the Jatropha oil being extracted. Jatropha oil is being extracted from the seed of the fruit of Jatropha. So it is the seed is being dried and then peeled and finally extract to get the oil. In my case, I didn't do the extraction. I just bought it from the company. So to make sure the quality is standard. Next. Okay, this is the background of my study. Okay, at the moment, most of the coating being used derived from petroleum-based chemicals such as epoxy, vinyl, acrylic, and others. So the using of petroleum-based chemical, since it is non-renewable, it will face the price fluctuation. So as an option, we try to replace the dependency of the petroleum-based chemical with the vegetable oil. So why we choose vegetable oil? Because vegetable oil consists of the unsaturated part, which can undergo chemical modification. So the advantages of vegetable oil is, first, it is a renewable source. Second, it is highly abundant. And finally, it is costly effective. Okay, for the material itself, which is Jatropha oil, for information, Jatropha oil, the scientific name is Jatropha curcas. In Malaysia, people also known as pokok jarak pagar. Actually, Jatropha is listed as the third important crops in Malaysia. The first one is palm, second one is rubber, and the third one is Jatropha. In Malaysia, the availability is around 600,000 acres in Malaysia, which is mostly in Sarawak. Okay, and then Jatropha oil is a non-edible oil that being used for coating application. For your information, there is another type oil that also being researched for coating, such as sunflower oil, linseed oil, and others oil, but most of them are edible oil. So these have negative impact to some people which don't agree where the edible source being used for non-edible application. So with the use of non-edible oil of Jatropha oil, we don't have any negative impact of that. Okay. Next, the jatropha oil contain of high unsaturated part, which is around 78%, and then which reflect its reactivity to undergo chemical modification. And then the optimum temperature is around 25 to 35 degrees, which is suitable in Malaysia. It is adaptable to low soil fertility and can sustain for 25 years. At the moment, this jatropha oil is being used traditionally as soap in cosmetic industry and organic fertilizer. Okay. So in my study, the jatropha oil will be converted into polyurethane acrylate. So what is polyurethane acrylate? Okay, polyurethane acrylate is a versatile resin for radiation curing base coating. The radiation curing allow the liquid form of the resin form a solid form that can be a coating. So this is given by the acrylate functional group of the polyurethane acrylate. Meanwhile, it also consists the soft segment, which is derived given by the polyol, which is OH functional group, and also the hard segment, which is by NCO group. So, why we want to use radiation curing technology? First, it is low emission of VOC, and then it is low energy consumption, and then third, it is very fast and high production rate, and it is consistent coating quality. Okay, below that is the basic reaction, which is the polyisocyanate. The NCO react with the polyol, which is the OH functional group, and we can get the polyurethane. Okay, next slide, please. Okay, so the main objective of this study is to synthesize the jatropha oil-based polyurethane acrylate, which is UA resin, for UV global coating application. So to achieve this main objective, this will cover the specific objective, which is first to prepare the jatropha oil-based polyol, which is JOL, via two-step reaction known as epoxidation and hydroxylation. And then second, we would like to study the reaction between the polyol with the aromatic isocyanate, which is 2,4-TDI. For your information, 2,4-TDI is commonly being used in the industry because it is very reactive. But bear in mind, it is also have adverse effect to our health, as it is linked to cancer. And we would like to compare 2,4-TDI with the cycloaliphatic isocyanate, which is IPDI. IPDI is a more safer option compared to 2,4-TDI. And the third one, we would like to characterize the physical and chemical properties of JPUA-TDI and JPUA-IPDI. Okay, next slide, please. Okay, this is the framework of the methodology. To prepare the JPUA, the first one, the crude jatropha oil that we have will undergo epoxidation reaction. So become epoxidized jatropha oil. So new resin is here, which is EGO. So EGO, at this step, we do characterization, which is OOC, oxygen, oxygen content, which is to determine how much COC functional group there. And then we measure the molecular weight using gel permeation chromatography, GPC, and also FTIR to detect the functional group of the related resin. Okay, after that, EGO is being converted into JOL, which is a jatropha polyol, using hydroxylation reaction. Here, the characterization is OOC, and then we have a hydroxyl value to measure how much how much hydroxyl have been developed, and then GPC and also FTIR. And then the next step is isocyanation. At here we have two parameters, two types of isocyanate, which is 2,4-TDI and IPDI. So 2,4-TDI with reaction with 2,4-TDI, it will become JPUA-TDI and JPUA-IPDI respectively. So the characterization will be FTIR, GPC, and TGA. Okay, next slide, please. Okay, this is the procedure to prepare the polyol. We have two steps here: epoxidation and hydroxylation. I don't want to go through each of step. I just want to mention that the molar ratio for jatropha oil, formic acid, and hydrogen peroxide is 1 to 0.6 to 1.7 molar ratio. So for auxiliary oxygen content testing, it is performed based on ASTM D165297. For hydroxylation, reaction was conducted with the reaction of methanol with acid catalyst. So for the hydroxyl value, we also refer to ASTM as listed there. Okay, next. Okay, next is measured based on molar ratio of 1, 1, and 1, which is a joule, the isocyanate, and HEMA. HEMA is the terminator, which can which will be at the acrylate function. The difference between the IPDI and TDI. For IPDI, we add some catalyst, which is 1% DPTDL to initiate the reaction. Okay, next. Next slide, please. Okay, okay, this is the result and discussion. Okay, for characterization, the crude jatropha oil is in orange color, it's like to brownish color. So that one is by visual determination. So to measure the color, we use calorimeter, which is the combination of red, yellow, blue, and neutral filter. So that is the exact color if we want to compare between each other. So basically, all resin are in liquid form except for JPUA-TDI, which is in semi-liquid and viscous form. Okay, the highest OOC that we achieve is 4.25%, while the hydroxyl value is 149.4. So, okay, next. Okay, this is the molecular weight. As we can see here, the molecular weight increase in each step of reaction. This indicates that the new functional group has been drafted to the backbone of the oil during each step of reaction. As a comparison between JPUA-TDI and JPUA-IPDI, the molecular of JPUA-TDI is double compared to JPUA-IPDI. This is due to the reactive reaction of the TDI, which contain the benzene ring. For the distribution of the is the average number of the molecule all have good distribution, which is nearest to 1, except for GPUA TDI, which is 2.15. This is due to the fast reaction of and the all-based polyol, which produce a bulk molecular weight which is very high, around 6,000, compared to its average molecular weight. So this explains why GUATDI is very viscous and it is in a semi-liquid form. Next. Okay, next. Next slide, please. Okay, this the proposed chemical structure on the left side during step 1 selection of polyol, and on the right side is spectra. So the jatropha oil in its original form, they have double bond, carbon double bond. So after we check under FTIR, the peak of carbon double bond is appear around 3,000 number. So the crude jatropha oil undergo epoxidation with hydrogen peroxide, and the peak of and the carbon double bond is converted into it was at the 800 peak of the desiccated one has to epoxy. That is oscillation where the COC ring will be break into to form the hydroxyl group, which is OH group. So new broad of OH group are detected at around 3,400 peak, indicate that the successful reaction of the hydroxylation. Okay, next. Next slide, please. Okay, this is the proposed reaction JPUA TDI and JPUA IPDI. Okay, the first step is isocyanation, which is addition of isocyanate, and the second one is acrylation, which is termination step with addition of acrylate functional group, which is derived from HEMA. Okay, next slide. Okay, this is the monitoring reaction during acrylation and during the isocyanation and acrylation reaction. Okay, as we can see, A is the polyol, which is the OH functional group, and then after we add some isocyanate, which is NCO group, new peak is there, which is around 2,200. This is peak of NCO, and then after 2 hours of reaction, the peak of NCO is disappeared, indicate that urethane link has been produced, which is 3,300, which is peak for NH, 1,700 for carbonyl, and then bending peak for NH also can be seen around 1,500. And the last one is the termination reaction, which is addition of acrylate group. Okay, the acrylate group is detected around 800 around 800 and also 1600. Both of them contain carbon double bond, which allow radical polymerization during radiation curing reaction. Okay, next slide, please. Okay, this is FTIR spectra of polyol, and compared with the both type of JPUA, which is JPUA IPDI and JPUA IPDI. Video, both JPUEI and JPUA TDI have similar pattern. This is due to same functional group of acrylate and also urethane. Okay, next. Okay, this is FTIR spectra under UV irradiation, which is after we exposed to UV and the sample being converted from liquid to solid form. As we can see here, there is this disappearance of acrylate peaks, which is around 1600, 800 and 660. So this indicates that all acrylate has been used up during the radical polymerization reaction. Okay, next. Okay, this is thermal properties, the decomposition of the JPUA TDI and JPUA IPDI under thermal gravimetric analysis. Okay, both have 3 steps of degradation. Okay, the first step is around 200 to 300 degrees Celsius, which indicate the decomposition of urethane bond, primary and secondary amines, olefin and dioxide. And then the second step occurred around 300 to 550 degrees, which is decomposition of chain season of the oil. And the beyond of 450 degrees, it is reflect the thermal oxidation of JPUA films. Okay, next. As a conclusion, 2 varieties of Jatropha polyurethane acrylate base isocyanate has been successfully synthesized, which is JPUA TDI and JPUA IPDI. JPUA TDI has higher viscosity and molar mass compared to JPUA IPDI. Both have similar degradation trend under TJA analysis, and both are found curable under UV irradiation and has potential in surface coating application. Okay, next. Okay, this is the list of reference for my study. Okay, next. Okay, I think that's all from me. Thank you.
Okay, thank you very much, Ms. Nurul Huda, for the great presentation and also research. So we're gonna go to the final and last presentation for this session. And this presentation is about overview of the vector-based neutron source for boron neutron capture trophy application. Without further ado, I invite Ms. Nur Faizan Muhammad Said. Please.
Okay. Bismillahirrahmanirrahim. Thank you very much, Mr. Chairman. Assalamualaikum warahmatullahi wabarakatuh. I'm Nur Faizan binti Muhammad Said, Research Director from Malaysian Nuclear Agency. Today I would like to present my paper entitled Overview of the Reactor-Based Neutron Source for Boron Neutron Capture Therapy Application. Okay, next. Okay, this is my presentation outline. I will start with the introduction and highlighting the two main components of the topic itself, which are the boron neutron capture therapy, which we also call as BNCT, and the reactor-based neutron source for BNCT. Then we will continue with examples of the reactor-based neutron source for BNCT using trigger research reactor, and end the presentation with the conclusion. Okay, next. Okay, in nuclear Malaysia, we have reactor trigger Puspati, which is a trigger Mark II research reactor. Around the reactor tank, we have what we call as outcore irradiation facilities. Okay, these irradiation facilities can be occupied with instrumentation for experiment and samples irradiations. So we have 4 beam ports and 1 thermal column. 3 beam ports have been occupied by the neutron neutron radiography facility, small angle neutron scattering, and neutron diffractometer facility. Another beam port is designated for prompt gamma neutron activation analysis and still under development. And we also have 1 thermal column which we plan and we propose to build the boron neutron capture therapy there. So this paper will basically a part of the knowledge acquisition for the proposal. So this paper aims to overview the BNCT basic principles and applications in general, then to identify the reactor-based neutron sources for BNCT, and to determine the beam properties, reactor, and the beam design, and other related parameters of trigger reactor-based neutron sources. Okay, next. Okay, what is boron neutron capture therapy? It is a radiation science based on nuclear reaction imaging, which used to treat cancer with poor prognosis, such as the glioblastoma multiforme, which is the high-grade brain tumor, melanoma, and head and neck cancer. This treatment is the combination of the targeting principles of chemotherapy and the localization principles of radiotherapy, with an advantage of reducing the destruction of neighboring healthy tissue. So in other words, we can say that BNCT is an alternative treatment for cancer that do not respond to standard therapy. Next. Okay, the basic principles of BNCT involve the nuclear reaction, with the main component is boron. Okay, boron will capture the neutron from the neutron sources and produce the lithium ions and alpha particles, and also the gamma radiations. As we can see in the next figure, it shows the locations or the conditions of the tumors cells before the BNCT and after BNCT. So according to Royal Society of Chemistry, the word boron is derived from the Arabic word burak. So the name explains the characteristic. So this in BNCT, we use the non-toxic boron 10 target drugs known as BPA that can selectively accumulate in cancer cells. The cancer cells have high demand of amino acid and often found in amino acid transporter. So this transporter is highly active, which makes it possible for to get 3 to 5 times more boron 10 into cancer cells compared to the normal cells. So when we bombard the neutron with the beam irradiation, the boron will capture the neutron and generates the lithium ions and alpha particles. These alpha particles is having high energy, and will destroy the tumor cells. Okay, next. So this is the procedure for the BNCT. As usual, the common procedure, the patient will need to go to the preliminary scanning, okay, to determine and calculate the tumor size and the volume. Okay, then after everything have been determined, we need to administer the boron compounds accordingly. After the injection of the boron compounds, the patient need to go through the PET scan imaging to check the uptake of the boron compounds by the tumor cells. If everything is according to the plan, next it will be the phase of the beam irradiation, either with the epidermal or the thermal neutron. And the final stage will be the lysis of the cancer cells. Next. Okay, we have two main sources for neutron sources for BNCT. Okay, at the early stage of the BNCT research and development, they only use reactor as the main sources because at that time only reactor can provide big amount of neutron at one time. It is pioneered by USA, Japan, and Europe. But when it comes to stage of clinical trials involving the patient and hospitals and all that, there is an inconvenient issues. Okay, so from that they suggested an accelerator neutron sources as an alternative. Okay, next. Okay, this is the example of the, this is the type of the reactor-based neutron source for BNCT. It can be from the existing reactors, either the reactor with large irradiation facility such as thermal column, or the existing reactors that having only narrow and long beam tubes. Okay, we also can get the neutron source from the newly developed reactors, newly built reactors, either conventional reactors or the reactors that dedicated for neutron capture therapy, and it can be from the thermal or fast reactors. So as I've mentioned earlier, in reactor Trigger Puspati, we have the thermal column. So I guess we are in the first category, which is the existing reactors with large irradiation facility. So we have that advantage of spectrum shifting and high flux to power ratio. However, we are separated from the hospital, and this facility might interfere with other surrounding utilization facility. Next. So, according to IAEA Tech Doc 1223, they suggested the beam properties, epidermal beams should be the best for the tumor that located deep into the tissues, while the thermal beams is sufficient for the tumors near the surface. Next. Okay, this variety or the variety of the neutron spectrum is important to determine the tumor that we are going to treat. Okay, as experienced by these listed reactors. Okay, the epidermal neutrons is good for brain tumor and head and neck tumor cancer, while the thermal neutron are good for melanoma and expanded liver cancer. Next. Okay, for the beam parameters, the IAEA Tech Dot 1223 has recommended, based on their technical meeting with all the BNCT facility owner, okay, the optimal epidermal beam intensity will be greater than 10 to the power of 9, and the gamma dose, neutron dose should be as less as we can get. Okay, next. Okay, for the beam design consideration, we must consider a few things. Okay, first, the beam intensity must have reasonably short irradiation time, because the patient need to be fixed in a position. So as shorter the time of irradiation, it will be better. Then second, the beam energy with high penetration capability to allow the treatment of deep-seated tumors, and the purity of the beam should not decrease the selectivity of the therapy, that is the reduction of fast and thermal neutrons contamination as well as from photons. Next. Okay, for general requirements to house a complete BNCT facility in reactor building, we need to consider sufficient and adequate fluence rate of neutrons that emanate through a large diameter beam tube. So we need to have a good shielding. Okay. Then second, we must have a suitable space at the exit side of the beam to accommodate a large working area for building the irradiation room. Okay, then we should also consider the freely accessible such that the patient who may be unable to walk or can be readily and easily brought into irradiation room from outside. Since we know reactor is a tight security area, so we need to consider this if we want to build the facility in our reactor building. Then there should be also space located outside the reactor building or within the building to house facilities for the reception and preparation of the patient before entering the facility. Okay, next. Okay, this is the suggested BNCT facility component. So we have number one is the reactor, which is the neutron source. Okay, then from the reactor we have the beam tube. Okay, then number three is the location of the patient in the irradiation room. Okay, so this size of irradiation room depends on what we plan to have. Okay, so if we plan to have a patient lying on the bed, so we need bigger room for the irradiation room. Okay, and number 5 is the control room. Number 6 is the reception area. While number 7, 8, and 9 are the beam dosimetry or characterization, beam monitors, and beam shutter area. Next. So for example, there are two I will highlight here, trigger research reactor that have been used as the neutron source for BNCT. Okay, first one is FIR Trigger Research Reactor in Finland, which is same with us. It has Trigger Mark II open tank reactor with graphite reflector with maximum steady state thermal power 250 kilowatt and the thermal neutron flux of 10 to the power of 13 neutron per cm per second per second. Okay. The operation of the reactor started in March 1962. First belonged to the Department of Technical Physics of the University of Helsinki and then Transfer Center of Finland in 1972. They started the BNCT irradiations in 1999, okay, when the license for patient treatment was granted to a company named Bonica Corporation until the company went bankrupt in 2012. Okay, then the Technical Research Center have decided to stop the BNCT irradiation due to high costs and the condition of the reactor itself, and the reactor has been really shut down in 2015. Next. Next, please. Okay, FIR, a nuclear research reactor, is proven to be a reliable neutron source because no patient have been because of a malfunction of the reactor, and over 300 cancer patients irradiated were in 1999, 2011, and all the patients should improve tumor control and survival. Okay, next. Next. Okay, Okay, the second research reactor is the Pavia Triga Mark II research reactor in Italy. They also have the Triga Mark II open tank reactor with graphite reflector. It started their operation in 1965. Okay, with maximum steady state of thermal power 250 kilowatt, and the thermal neutron flux of 10 to the power of 6 to 10 to the power of 10. It is located University of Power Study Irradiation 2001 with modified thermal column. Okay, next. Okay, in 2001, which is the first treatment of multiple hepatic metastasis from colon by BNCT and auto-transplantation technique. Okay, the liver was extracted after the boron infusion, irradiated in the thermal column of the reactor and re-implanted in the patient. So 2 patients were treated, demonstrating the feasibility of the therapy and the efficiency is destroying the tumoral modules, sparing the healthy tissues. So basically it is good results and positive results, and they proceed with the NCT irradiations until now. Okay, next. So as a conclusion, okay, number one, there's an advantage of trigger design for BNCT include large flux per watt per power feature and inherent safety of the trigger fuel. And we know trigger reactor is one of the safest research reactor. So due to the strong and fast negative temperature coefficient of the reactivity of the trigger fuel and easy operation of this type of relatively safe neutron source for a clinical BNCT facility. Okay, number 2, the required beam intensity and average neutron energy must be within the requirements, which themselves can vary depending on the type of tumor we want to treat. Okay, and the last one, even though most of the reactor-based neutron sources for BNCT has been permanently closed or decommissioned, the future of BNCT applications is still widely open and is still a hot topic to be explored, and still giving a huge impact and contribution to the field. Thank you.
Thank you very much, Ms. Nofaiza, for the great presentation on BNCT. I hope we can collaborate in the future for development of BNCT in Malaysia. And this is our last presentation. So after this, we have a Kahoot challenge, and the code is 1460646. I repeat, 1460646. I repeat again, 1460646. So you can enjoy yourself playing a Kahoot challenge. So we can, after this, we go to the lunch break and poster session during the lunch break, and we can back again on 2 p.m. That's all. I'm so sorry, and if we have going to the technical issue and other, and thank you very much to all the crew for iNuSTEC 2020. Assalamualaikum. See you soon.
interrupt this program to bring you a special news bulletin. The Japanese have attacked Pearl Harbor, Hawaii by air, President Roosevelt has just announced. The attack also was made on all naval and military activities.
Perkara yang nak saya ceritakan ini perkara yang saya alami sendiri, yang saya tengok sendiri, yang saya rasa sendiri, bukan ambil daripada bacaan-bacaan mana tidak. Itu yang saya nak ceritakan. Yang pertama sekali, bagaimana saya boleh sampai ke sana? Bila Jepun darat ke tanah Melayu, semua orang mesti belajar bahasa Jepun. Bahasa Inggeris tak boleh. Satu cakap bahasa Inggeris lelapangnya. Bahasa Melayu okey, bahasa Jepun mesti belajar. Jadi itulah diantaranya. Orang yang dihantar belajar bahasa Jepun ini ialah guru sekolah dan pegawai MCS, supaya orang ini dapat menyampaikan, mengembangkan bahasa Jepun ini ke sekolah-sekolah dan ke pejabat-pejabat kerajaan. Belajar di Kuala Lumpur 3 bulan. 3 bulan belajar. Boleh cakap. Takut kena lempang. Belajar sungguh-sungguh. Sebab itu bila JPA nak mengadakan kursus dasar pandang ke timur, tanya saya, cikgu, berapa lama kita buat kursus ni, cikgu? 3 bulan? 3 bulan boleh? Boleh. Tapi caranya lempang je lah. Oh, tak boleh lah, cikgu. Kalau tak boleh, 6 bulan. Sebab itu dasar pandang ke timur yang dibuat di ITM ni 6 bulan. Belajar. Di Kuala Lumpur belajar 3 bulan, kemudian dihantar ke apa? Ke Melaka. Ya. Melaka belajar 6 bulan. Belajar 6 bulan di Melaka. Antara orang yang terbaik, saya termasuk salah seorang yang terbaik. 10 orang jadi guru penolong, membantu guru Jepun. Guru Jepun bukan semuanya di Transka, sebab intake yang tak beramai, bantu lagi, bantu guru Jepun. Jadi saya duduk di Melaka belajar bahasa Jepun setahun. Jadi apa? Belajar bahasa Jepun, balik kerja di pejabat pelajaran, buat kurikulum bahasa Jepun. Buat kurikulum bahasa Jepun untuk sekolah-sekolah di Kuala Lumpur. Kemudian itu dipikirkan mau hantar, elok dihantar, yang baik ni dihantar pergi masuk ke universiti, balik jadi pegawai pelajaran. Jadi dihantar 15 orang, jadi inilah 4 orang. 4 orang ni yang dipilih untuk 4 orang yang dipilih untuk pergi ke Jepun, belajar bahasa Jepun untuk mengambil ijazah. 4 orang. Sampai ke Jepun, di Pra University di Tokyo setahun. Sebelum masuk ke universiti. Sebab apa Jepun? Profesornya, dia naik ada pentas, dia mula mengajar, tutup beli mata, dia bercakap macam bullet train. Jadi kalau kita tak ada asas bahasa Jepun yang baik, Kita tak tahu apa benda yang cakap kan. Tutup pintu mata dia pergi kita. Buka pintu mata, warik habis. Kita tengah mana kalau tak ada background apa yang baik. Melainkan kita terpaksa campur dengan apa? Campur dengan apa benda-benda pun tanya apa benda yang ini. Kalau tidak, tinggalkan kita. Itu caranya. Jadi belajar di Tokyo, Pra University, setahun. Itu ada cerita tadi kita tengok. Bila terberikat, mereka naik Okinawa. Jadi kawan di Okinawa, daripada Okinawa terbang ke Tokyo. Kapal terbang B-29. Tiap-tiap hari pukul 3 petang. Tiap-tiap hari pukul 3 petang dia terbang dari Okinawa sampai Tokyo di bomnya. Kami tengok kan. Itulah mudahnya saya tengok bom. Bomnya habis keliling tempat bandar-bandar di Tokyo. Bom lagi, bomnya lagi. Tiap-tiap petang. Kemudian apabila dah sudah Pra University setahun, masuk ke Universiti Hiroshima, tak ada kapal terbang musuh, kapal terbang mereka tak ada langsung. Elok, relax kita ni. Tak macam di Tokyo. Hari datang kapal terbang musuh. Ini Hiroshima tak ada apa-apa. Rupanya tak ada apa-apa tu, dia nak bagi bom yang special. Inilah pelajar yang pergi ni bukan semua yang pergi ke Hiroshima. Yang ambil pendidikan saja, dia ambil pendidikan. Jadi yang ambil pendidikan di Hiroshima, Yusuf dari Pertahanan, Syed Omar, Al-Sakov, Abang Ipar kepada Engku Aziz, Abang Ipar Engku Aziz daripada Johor, dan saya. 3 orang. Itulah 3 orang yang belajar di Hiroshima. Belajar dan jadi mengambil ijazah pendidikan. 6 hari bulan 8 hari ni 6 hari bulan 8 tarikh yang sama, pukul 8.15 pagi. Masa itu saya ada mathematics, pelajar kelas mathematics. Pergilah saya kelas matematik. Kelas matematik saya tu pula tidak di main building, tapi di building music, di bangunan music. Bangunan music tu pula dibuat daripada kayu. Main building tu ya konkret. Yang dua lagi ni, yang dua lagi tadi tu saya rumah dengan Yusuf. Dia tak ada kuliah. Tinggal di asrama saya. Nanti dia akan cerita. Saya pergi lah. Boleh. 8.15 berbunyi siren. Bunyi siren. Tadi laki dia pun. Bila bunyi siren, masuk dalam rumah. Shelter tu dekat betul dengan apa? Dengan building musik. Masuk dekat tu. Agak sini lebih kurang 20 minit kat dalam shelter. Mereka bunyi lagi. Clear. Kami pun keluar. Masuk ke apa? Ke classroom. 2 kawan saya ni di permayaan tak ada kelas. Jadi saya dengan penyiaran Yusuf daripada Brunei dan dengan Profesor Tola, Profesor Mathematics. 3 orang dalam kelas. 3 orang dalam kelas ni duduk. Saya elok-elok duduk je. Saya elok duduk je. Mula je Profesor tu mengajar, cahaya melalui cermin. Bila melalui cermin, saya terpanjat. Saya kata dengan kawan saya berkenan, Yusuf, kilat. Bila kata kilat dia, habis. Tak tahu apa cerita ni. Tutup. Bangunan tu tutup. Ni dia tanya dia berapa lama. Saya tunggu berapa lama di bawah runtuhan rumah tu tak tahu berapa lama. Tak setengah jam, tak sejam, tak 2 minit. Cuma yang saya tahu, saya nampak, saya sedar agaknya, saya nampak cahaya. Sila-sila runtuhan bangunan itu nampak cahaya. Mengangkat, keluar. Ikut cahaya itu, keluar tengok. Baju berdarah, penuh darah. Kejap lagi pengira Yusuf keluar, kejap lagi Profesor Toda keluar. Berdarah. Di mana ada? Tengok badan tak ada. Rupanya darah di kepala. Agaknya masa duduk menengah kuliah tu, jatuh. Bangunan tu runtuh, mengkali kayu yang kecil agaknya kena di kepala, itu saja yang berdarah. Dia kesana. Kalau kena lah kayu yang besar, penyet, tak dapat cerita ni. Kuasa Tuhan izinkan saya selamat berdarah. Kemudian tu tengok di bawah, keluar kita tengok di luar, terang macam ni. Yang ada bangunan-bangunan konkret dia, tak ada rumah-rumah. Apa benda ni? Di Tokyo, kita tengok Okinawa datang daripada Okinawa, kita nampak ada bangunan-bangunan keliling tu ada, cuma yang bom tu di mana dia gugurkan bom, dia keliling-keliling tu saja yang rosak. Tapi tidaklah seluas ini. Safar-safar pada jarak pada tubuhku. Baik, sudah macam itu, kata Profesor, balik berdorang, balik ke asrama. Balik ke asrama, petang, bagi tahu datang balik ke universiti, bagi tahu buat laporan, apa yang ada, apa yang tak ada, apa jadi. Ya, nak balik dah punya susah. Dah timbulan macam itu, pokok dah tumbang, rumah dah tumbang, nak cari jalan balik pun dah tak tahu. Tak tahu mana jalan. Itu satu hal. Yang kedua, dia jemput. Yang mana hidup lagi menjerit-jerit. Tolong yang tersempit di bawah rumah, yang kaki dah patah. Macam mana kita nak nolong dia? Kita pun nak pergi tengok kawan yang dia asrama. Cubalah angkat, cari lompat sampai ke asrama. Tengok, ni ada lagi. Yang untuk ni bangunan ni ada lagi. Sebagai tanda kenang-kenangan bom atom. Kalau pergi ke sana, ada lagi bangunan ni. Macam itulah keadaannya semua. Okay? Jadi yang menjadikan hampir runtuh sekali gegaran bom tadi 3 meter. Jadi dia jatuh, kami dapat tahu kemudian, kalau dia jatuh ke tanah, ditahan di tanah, tak ada banyak kerosakannya. Rupanya bila dikukuhkannya bom dengan parachute, dikukuh dengan parachute, orang yang menjaga ni pun tak tahu dia ingatkan parachute ni orang turun agaknya. Jadi dibunyikan dia, kemudian tu sampai tengah, meletup. Bila meletup, sebab itulah radius itu. Radius tu macam besar, lebar. Itu disebab anak yang apa? Gegaran itu kuat dan radiusnya lebar. Habis semua untuk. Kemudian kita tahu. Kemudian itu dah sebab jadi begitu. Jadi, bila gegaran yang kuat, misalnya sinema, bagaimana bawah alam, habis. Bengkok-bengkok begitu. Dia lagi. Train. Tinggal langka jadi. Celah-celah pokok yang tumbang itu kami punya lelah nak balik ke asrama. Tu pergi. Dalam masa nak balik ke asrama tu, saya ambil Yusuf ni, jumpalah ni Yusuf. Jumpa ni Yusuf di tengah jalan. Razak, tolong kawan di asrama. Aku sihat, kata dia. Dia lari daripada asrama, daripada dia lari arah ke bandar. Bila sampai ke kawasan asrama, aku nak cari mana asrama. Asrama pun tak kenal, sebab semua dah tumbang dah rata ya. Jadi agak-agak oh ini agak asrama. Kaget. Bahasa makcik ibu asrama, ada ibu asrama. Bahasa itu ialah salah seorang daripada pegawai sebuah syarikat di sebelah asrama. Mengagakkan kami kata lah. Kapan kita buka batu ni semua, buang-buang batu betul ni semua, kita dapat ruang satu besar, kita tarik. Tarik. 9 tarik. Tarik tengok matanya penuh dengan kaca. Sebab dia pakai gelas, beku. Apa ni, darah beku. Apa? Tarik dia letak luar. Barulah kita dapat pedoman. Seberang itu, sebelah tu jalan, sebelah jalan tu barulah dapat asrama. Jadi, pergilah ke asrama. Tolong kawan. Tolong kawan. Dan orang-orang Jepun juga. Orang-orang Jepun bersama, tarik. Yang mana tak boleh, apa jalan kita letakkan sebelah. Badan saya lebih kurang macam ni lah, lebih baik gemuk sikit agaknya. Boleh angkat orang Jepun. Tak orang Jepun angkat kawan letak ke sebelah kaki. Yang itu pergi ke apa? Pergi ke asrama, ambil buku-buku, gambar-gambar. Nak bawa balik masukkan power set. Semua tak ada. Masa membuat kerja itu, ini asrama. Depan sungai. Seberang sana dah mula membakar. Oh, bakar. Macam saya dulu. Oh, bakar. Bila dia mula membakar, orang di sebelah sana nak lari ke depan, dikejar. Lagi. Nak lari ke belakang, mati. Habis apa tuan? Terjun masuk sungai. Terjun masuk sungai, dekat tebing. Sandar dekat tebing. Terjun itu depan air. Bawa air nanti, sandar dekat tebing. Dekat tebing sungai. Orang ni pun masa pegang universiti studentnya yang perempuan semua buat kerja JKR, pergi satu mana membersihkan sampah-sampah, buang sampah, cuci apa longgang, cuci jalan. Student perempuan, student lelaki nolong askar. Jadi itu kerja dua. Jadi hari itu Hiroshima ada student perempuan dia ke tempat lain datang. Jadi sebelah sana api membakar. Bila mula membakar, orang semua dia duduk di tebing, dia bakarnya orang dekat tebing. Bakar orang, ini bukan cerita saya tengok, saya seberang sini. Tengok api sebelah sana. Tengok sendiri, tak ada. Dibakarnya. Oh. Itu dalam air. Di bawah air. Jadi api itu makin lama ke depan. Ke depan. Ada jembatan lagi sebelah sana. Di sebelah jembatan. Datanglah dari tempat kami. Api itu datang. Bila datang ke tempat kami, apa nak buat? Kita dah tahu dah, kita dah tengok macam mana api membakar orang di sebelah sana. Jadi kita di sini apa? Dah tentu kena macam tu. Jadi, ini konsekuan. Saya lari pergi dekat sungai, dekat jambatan. Saya tengok ada rakit. Ada rakit terikat di situ. Tuan-tuan, beri rakit. Beri rakit terikat di situ. Jadi angkat. Saya nak besok yang dua dia kagaan. Angkat. Angkat ke kawan, tak ke rakit. Angkat orang Jepun, dia tak ke rakit. Sebab api yang boleh datang. Ambil power set dari mana-mana kami selamatkan sikit barang. Tak ke rakit. Yang paling sedih sekali, ibu asrama. Ibu ibu asrama yang sunnah. Masa saya pergi ke ibu asrama tu, tengok ibu asrama tu di bawah, dia boleh berjalan-jalan lagi. Sebab dia tak kena peruntukan asrama tu, tak kena pada dia boleh berjalan. Jadi dia terasa, aku tak apalah, biarkan. Cari kakak engkau anak dia. Api mula datang. Dia di situ. Jadi kami cuba tarik batu tak kedaya lagi. Kira dari pagi sampai dekat tengah hari, nolong orang nak itu ini semua. Badan nak letih, nak tarikkan batu keluar cuma tak ada daya. Api dia makin dekat, tidak ada. Tapi tak bagi tahu kita api datang. Nak bakar api. Jadi duduk tak selama. Api datang bakar. Bakar. Jadi api ini punya dia tak hati memang manusia hidup. Kami terakit dulu, kami tengok api bakar. Dia jadi macam cyclone gitu. Dia sembar yang kami terakit. Kami yang terakit itu sembar api. Tapi boleh buat terjun. Kalau berjakar, tidaklah benar. Pegang api. Habis nafas, balik. Dan 3 kali dia dapat kali dia. Tengok haversack yang dia ambil tadi dah terbakar. Dah terbakar. Menjerit lagi saya ni menjerit. Usuk. Rakit terbakar saya. Bila esok ibu naik, tendang dengan haversack ke jatuh. Dalam sungai tu. Sampai api tu dah lari jauh, barulah kami yang 7 ni tadi semua naik duduk balik. Foreign students semua ada. Kecuali Yusuf tadi yang lari ke bandar. Tapi orang Jepun, mana yang kaki sakit, mana yang kaki apa bakar, lecok dan sebagainya, dia terjun tu dia tak boleh naik lagi dah. Jadi bawa air. Di dalam orang Jepun dia pun. Jadi kami dia duduk kat situ sampai api tu dah lari jauh, barulah kami naik. Dekat situ ada jambatan, kami bersihkan jambatan, naik ke jambatan. Naik jambatan, duduk kat jambatan. Nanti kan kaki tu dah pergi jauh. Bila duduk kat jambatan tu, kenanglah pesan daripada profesor tadi datang. Pergi kawan saya punya dia suruh pergi ke universiti melaporkan diri. Nantikan ni esok tak ada. Yang lain semuanya orang suka. Jadi di universiti dia bagi apa? Bagi beras. Bawa balik dia esok ni tadi. Beras penuh dengan kaca. Agaknya stor beras tu dekat dengan tingkat. Habis universiti dia dah bergerak, kaca semua masuk dalam tempat beras tu. Bawa balik beras. Letak beras. Nanti ingat, nanti nak dimakan, nak buat masak nasi. Pilih kaca-kaca yang besar-besar. Kita nampak kecil-kecil ni yang cerita. Dalam pada tengah itu, orang mula lapar. Jangan daripada pagi, dia dah tengah hari dah. Penat tak lagi. Lalu ayam putih. Seekor ayam putih lalu. Kejar, sup. Kita buat sup. Tangkap dia. Cita-cita makin tinggi lagi. Tangkap ayam putih ni tadi. Tangkap. Kapan? Sebenarnya pisau tak ada. Ambil paku ni. Ambil paku. Cucuk paku ni nak punya beli ayam dengan paku tak mahu dia mati dah. Dan saya cuba tu. Cucuk tak mahu mati. Ada mahu mati tak kosong. Simpan. Dekat. Simpan sini. Besok dia buat. Dah lama. Lepas tu, dah malam sikit, barulah terdengar suara. Saya kata tadi, budak-budak perempuan, sekolah menengah, membersihkan jalan. Buat kerja-kerja, dengar mak bapak datang, mencari anak. Neko-chan, memanggil anak. Mana ada anak lagi? Kita tak tahu dia mak bapak dia datang dia pergi tempat lain, bukan di apa di Hiroshima tu mencari anak. Kemudian kita ada kita dengar pula baru ada orang boleh masuk, dah api dah reda dah pergi tempat lain kan, baru ada orang boleh masuk. Tidak, mana macam masuk kan sebab pun tak ada api hilang-hilang. Yang kita datang yang Red Cross bawa putih kering, bawa ubat bagian dengan kemudian tu satu lagi pula yang dengar saya, Mizu kudasai, tolong bagi air, kata dia. So, orang minta air, mana kita bagi air? Ambil air sungai, di tempatnya tu, bagi air. Di celah-celah keuntungan tadi, tu, bagi air minum 10 minit mati. Bagi orang lain minum 10 minit mati. Awak bukan hari sains, saya tahu benda tu. So, air kotor mati banyak lalu sebaik kotor. Kita tepus, ambil air tepus, sejukkan, bagi mati juga. Yang itu cakap dengan dia, jangan minum air. Kalau minum air, awak mati. Kata dia takut. Dia lah mati kerana minum air. Yang itu saya kata, berusup, jangan sup. Jangan beli air. Kita jadi kumpul nombor 2. Pasal mati, kumpulnya dia radioaktif tu, panas di dalam. Itu satu tragedi yang kami sendiri dah lalui dia. Bila hari besok ke malam dah, besok syaraf berkesan, Profesor Berkesan datang ke apa? Ke kampus. Ya, kita nak pergi ke kampus. Cari ni Yusuf ni tak ada, ni Yusuf seorang yang tak ada, lain semua ada. Jadi pergi mencari ni Yusuf. Inilah yang saya dapat tahu. Saya dapat tengok sendiri dengan mata saya macam mana deritanya mangsa-mangsa bawah. Dia cari. Jumpa warden yang lari sama dengan dia. Dengan dia tu, muka saya tak kenal saya warden. Muka dia dah kembang, macam bubur baking powder buat kek kembang. Tak kenal muka dia. Cuma saya kenal dia warden sebab dia pakai tali pinggang, bakal tali pinggang. Yusuf ni mana ke? Pergilah cari. Macam mana nak mencari orang mati lah, menimpun, lipat. Pertama sekali di hospital. Pergi saya ke hospital juga. Orang fikir kan tempat lain kena, hospital ni tak ada apa-apa, pergi tunggu hospital. Yang tidak pertolongan. Itulah secara ringkas. Jadi nak tahu secara panjangnya ni. Dia masa dah bagi soal satu, dah ada. Alhamdulillah, sifat dia dewan bahasa sampai nyari. Kita dah tak ada jual, sekolah pun tak ada. Bila saya berceramah macam ni, saya tunjuk buku ni. Dewan bahasa terdekat buku debu risma cerita saya penuh lah ni. Patutlah ada di perpustakaan, patutlah ada sekolah-sekolah. Di mana cikgu? Kira-kira tak ada. Di mana ada dewan bahasa? Ini dia baginya sama satu ya. Tak laku kan ya. Kemudian Kemudian buku ini anak murid saya orang Jepun dia kata Razak kata dia aku nak terjemahkan dalam bahasa Jepun. Terjemahkan dalam bahasa dia terjemahkan dalam bahasa Jepun. Dinamakannya Waga Kokoro no Hiroshima. Hiroshima dalam kenangan itu. Jadi satu karya yang aku di sini kalau kita perhatikan kulit ni ini burung. Apa namanya sayap burung merpati. Burung merpati, bulu burung merpati dijadikan simbol di sini. Kenapa? Dia cerita tu. Jadi bila 6 bila saya pergi negeri pun dia adakan himpunan sorsoran. Kemudian tu Lord Mayornya kepada yang membaca damaian. Lepas itu lepaskan burung merpati. Lepaskan burung merpati, kebang semua burung merpati. Semua mesti bangun. Saya perhatikan satu burung merpati sayap itu, bulunya itu tanggal kebang itu. Saya pun ada tangan. Tak ada saya kejar. Saya tak ada tangan tempat berdiri saya tak ada tangan. Dia kebang, jatuh ke dalam saya. Burung ni burung merpati jatuh ke dalam saya. Jepunnya heran lah. Yang di kanan saya ni, mampu kata dia. Apa sebab? Mampu dia jatuh ke dalam kau. Sebab akal aku cintakan kedamaian.
Minggu lalu, Panorama 1 telah menyiarkan bahanan nuklear terhadap dunia. Minggu ini, nuklear akan mengupas mengenai kegunaannya untuk kesejahteraan. Penggunaannya meluas sebagai sumber tenaga teknik dalam rawatan barah sehinggalah penggunaannya untuk mengesan di bawah tanah. Rawatan barah umpamanya, nuklear memberi harapan baru kepada pesakit. Sejak peristiwa gugurnya bom atom di Hiroshima dan Nagasaki, Jepun, nuklear dianggap oleh masyarakat dunia sebagai bahan ngeri yang tidak ada manfaat langsung terhadap manusia. Begitulah apabila kelebihan yang diberi kepada akal manusia disalahgunakan untuk kepentingan pemimpin negara maju.
Kesihatan merupakan salah satu daripada kegunaan awal nuklear. Umpamanya X-ray dan kemudian imbasan untuk organ-organ dalam badan, dan juga perubatan nuklear digunakan untuk diagnosis dan juga terapeutik, pengubatan dan pengesanan penyakit di badan. Umpamanya di Malaysia sendiri bidang ini dah berkembang luas.
Kaedah menggunakan nuklear melalui pancaran radiasi telah diperkenalkan dalam perubatan, terutamanya dalam merawat kanser atau barah. Kanser merupakan satu daripada masalah serius mengenai kesihatan manusia, kedua terbesar selepas penyakit jantung. Kanser terjadi akibat pertumbuhan sel yang gagal dikawal ataupun pertumbuhan yang luar biasa. Kanser boleh terjadi di mana-mana sahaja dalam anggota badan manusia, seperti kanser darah atau leukemia, kanser tulang, kanser kulit, kanser gusi, payudara, kanser rahim dan kanser otak. Dan lebih setengah abad yang lalu, kaedah nuklear ditemui untuk merawat penyakit ini. Pancaran sinar X yang dipanggil radioterapi didapati mampu membunuh sel-sel kanser. Malah melalui kaedah sinar X ini, kedudukan kanser dapat ditentukan dengan tepat. Orang ramai selalunya fobia terhadap sinar X ini yang dipercayai akan memberi kesan sampingan terhadap kesihatan. Namun, kaedah inilah satu-satunya yang dapat mengesan kedudukan parah dan mengawal daripada merebak.
Punca cobalt 60 ini digunakan di pusat radioterapi untuk tujuan memberi rawatan kepada kanser. Jadi pihak hospital, dia ada setengah hospital dia menggunakan punca ini untuk merawat kanser. Jadi keluaran ataupun output daripada punca ini perlu diukur dengan tepat sebelum sinaran itu deliver pada pasien.
Ada kalanya pesakit terpaksa menjalani kedua-dua kaedah bagi rawatan kanser, iaitu pembedahan dan radioterapi, dan ia pastinya akan mengambil masa yang agak lama dan kosnya agak tinggi. Penggunaan radioterapi sinar X membolehkan doktor dapat mengesan tumor kanser lebih jauh di dalam badan menggunakan gelombang bunyi dan komputer yang dipanggil sebagai Computerized Axial Tomography atau CAT scan.
Sebab masalah yang terbesar dia orang takut. Kenapa dia orang takut? Sebab dia orang dengar cerita. Cerita apa? Itulah kalau ni dapat kanser, kan orang potong ni potong tu, habis tu mahal lah, habis tu tak payah buat semua ni, pergi kat bomo ke, cuba makan-makan nutrition ni. So dia orang confused, kebanyakan dia orang confused.
Semakin hari semakin ramai penghidap kanser seluruh dunia, termasuklah di Malaysia, dan kanser payudara antara pembunuh utama kaum wanita. Untuk menangani gejala ini, Majlis Kanser Negara, ringkasnya MAKNA, telah ditubuhkan bagi membantu golongan pesakit. Tujuannya bukan sahaja memberi rawatan, tetapi juga memberi kaunseling kepada pesakit dan kaum keluarga.
Perkhidmatan yang disediakan di Institut Kanser MAKNA HUKM ialah radioterapi, surgery dan kemoterapi. Itu untuk onkologi. Tapi kalau untuk leukemia, bone marrow transplant ataupun stem cell transplant.
MAKNA juga menerima sumbangan orang ramai dan badan kebajikan, termasuklah keuangan, mesin-mesin dan juga semangat. Walaupun di hospital tertentu ada rawatan kanser, tetapi di MAKNA, pesakit diberi perhatian khusus dari segi pemeriksaan, perubatan dan kegiatan harian. Tidak kesemua kaki tangan MAKNA bergaji tetap di sini. Mereka juga adalah dari golongan sukarelawan, bukan sahaja para doktor dan jururawat, tetapi juga orang awam yang mengambil berat terhadap pesakit ini. Dan dimakna juga turut dibekalkan mesin mengesan dan perubatan teknologi nuklear. Kaedah sinar X atau X-ray antara peralatan penting dalam perubatan kini. Sinar X ini dapat mengesan bahagian di dalam badan. Ada 4 bahagian asas di dalam badan yang boleh dianalisis menggunakan sinar X. Bahagian tulang atau tisu lembut seperti pembuluh darah dan organ-organ di dalam badan atau lemak serta udara seperti di dalam paru-paru. Banyak kegunaan nuklear yang semakin hari semakin berkembang. Kaedah sinaran radiasi nuklear bukan sahaja semakin perlu dalam perubatan tetapi juga dalam teknologi lain seperti imbasan di dalam tanah, penghasilan tenaga dan yang terbaru, teknik pengayonan yang membolehkan bahan makanan disimpan lama. Teknik pengayonan ini telah diguna pakai lebih 40 negara dan ia banyak menggantikan teknik penggunaan bahan kimia.
Saya rasa tujuan kita, salah satu daripada tujuan kita ini ialah untuk menyedarkan orang ramai bahawa dalam setiap teknologi itu dia mempunyai 2 side, positif dan negatif. Cumanya dalam nuklear ini negatifnya lebih diketahui ramai. Kadang-kadang kita khawatir juga apabila yang negatif ini diketengahkan terlalu banyak, maka kita mungkin orang kata menarik diri daripada untuk mempelajari dan mengetahui yang positifnya. Jadi kita berharap dengan menonjolkan positif dan negatif ini, ramai yang akan mengetahui bahawa yes, nuklear, mana-mana semacam teknologi lain ada positif dan negatif, terpulanglah kepada kita. Dan sebagai orang yang bertanggungjawab dan bermoral, kita hanya mengambil yang positif.
Kini tiba masanya manusia mengambil langkah positif terhadap nuklear. Peristiwa di Hiroshima dan Nagasaki jangan diulang lagi. Nuklear tidak harus dijadikan sebagai perlumbaan senjata dan pengukur siapa kuat di dunia ini. Nuklear seharusnya menjadi bahan mesra yang membawa manfaat terhadap manusia seluruh dunia. bom atom, senjata nuklear yang paling digeruni, pernah menjadikan Hiroshima dan Nagasaki padang jarak padang terkukur. Kini ia juga sebagai pengukur kekuatan negara yang memilikinya dan bukan semua negara boleh atau dibenarkan membina senjata ini. Nuklear, pengalaman yang cukup mengerikan.
6 Ogos 1945, pesawat B-29 yang dinamakan Enola Gay berlegar di ruang udara Hiroshima, Jepun. Senjata jenis uranium-235 yang digelar sebagai Little Boy telah digugurkan di bumi ini pada jarak 1,900 kaki atau 640 meter. Akibatnya, 2/3 bandar ini musnah, meliputi kawasan seluas 10 km persegi. Kesannya, 140,000 jiwa daripada 350,000 rakyat bandar ini terkorban. Sempena Hari Nuklear Sedunia pada 6 Ogos ini, kru Panorama 1 meninjau sejarah silam pengeboman di Hiroshima dan Nagasaki bersama Pangeran Yusuf, salah seorang mangsa yang terselamat.
Pagi itu, sebelum pukul 6, ada siren mengatakan ada alamat serangan udara. Jadi kami semua keluar, masuk ke dalam shelter, ataupun dalam bahasa Jepunnya bukugo kata, masuk dalam itu. Keluar atas alamat lepas itu ada satu alamat lagi baru, alamat siren bunyi, tekniknya serangan udara sudah tak ada lagi.
Tidak ada seorang pun yang menduga bahana yang akan menimpa mereka.
The moment saya masuk ke dalam bilik lecture tu, saya tengok penuntut sudah ada, profesor ataupun sudah. Jadi saya terpaksalah menundukkan kepala, minta maaf, boleh kata, duduk. Wallahualam, tak tahu berapa saat lepas, berapa minit lepas itu, tiba-tiba dengan serta merta dengar satu bunyi dahsyat sekali.
Bola api yang menjulang ke udara menyebabkan suhu naik mendadak sehingga berjuta darjah, yang pastinya meranapkan apa saja di kawasan sekitarnya. Malah bola api seumpama cendawan raksasa akan membawa apa saja sama ada debu dan lumpur yang menyebabkan pencemaran teruk. Letupan bom atom mengakibatkan bangunan runtuh walaupun terletak berbatu-batu jauhnya. Kesannya amat dahsyat sekali. Radiasi ini bertahan lama menyebabkan pencemaran meluas ke udara, air dan ladang. Partikel yang kekal dengan radioaktif mampu bertahan begitu lama sehingga 1 abad. Sesiapa yang terkena atau termakan akan menyebabkan parah dan risiko mendapat anak cacat.
Pergi ke sana dengan sedaya upaya menolong orang minta tolong ni, mengangkat mereka yang ada. Tak boleh saya bayangkan, ada yang melucut segala-gala, kaca pun ada di badan yang kena diangkat, selamatkan mereka. Ada yang ditaruh di tepi bantai, tepi tebing tu, ada yang dimasukkan di rakit tu.
Selain itu, letupan nuklear juga menggugat sistem udara dunia, termasuklah atmosfera dan angkasa lepas. Hiroshima dan Nagasaki telah mengajar begitu ngeri bahana nuklear. Tidak dapat dibayangkan berapa ramai yang mati dan menanggung derita sehingga ke hari ini.
Cuba kalau senjata-senjata moden, yang modern weapon gunakan untuk faedah membaiki, membuat senjata untuk keamanan dunia, untuk kebaikan perusahaan, industri dan ubat-ubatan. Banyak boleh dibuat. Bukan untuk membunuh orang yang tak berdosa.
Penggunaannya telah menular di pelbagai sektor lah. Bermula daripada perubatan, industri alam sekitar dan sebagainya, dan juga agriculture. Dan kita dapati ramai dah yang mengetahui bahawa nuklear ini bukan saja mendatang keburukan, tetapi juga banyak kebaikannya. Jadi saya rasa salah satu yang positif.
Selepas tragedi Hiroshima dan Nagasaki, manusia tidak pernah serik. Perlumbaan memiliki senjata ini menular di merata negara, terutama kuasa besar. Senjata nuklear menjadi pengukur kekuatan perang dingin antara Soviet Union dan Amerika. Rusia menguji senjata nuklearnya pada 29 Ogos 1949. Britain pula pada 3 Oktober 1952. Diikuti oleh Perancis pada 13 Februari 1960 dan China pada 16 Oktober 1964. Dalam pada itu, kuasa besar ini seolah-olah melantik diri sendiri, menuding jari ke arah sesiapa sahaja, sama ada mereka berhak atau tidak untuk membina senjata ini.
Kalau boleh, pemuda sekarang, bukan pemuda Melayu, bukan pemuda seluruh dunia, mengenal bahawa mereka inginkan keamanan. Kalau pemuda, sebab bagaimanapun orang mereka tenaganya untuk membunuh, kalau pemuda refuse, tidak mau berperang, dunia akan aman.
Tidak ada satu pun negara yang terlepas dari bahan nuklear. Kesilapan yang sedikit akan membawa padah yang besar jika senjata ini meletup ataupun bocor. Dunia kini memang tidak selamat dan tidak mustahil kenangan silam kembali menjelma di kerakusan manusia itu sendiri.
Jika tadi Panorama 1 telah mengupas kejamnya senjata nuklear, tetapi di sebalik itu, nuklear ada manfaatnya. Untuk mengetahuinya, tunggu minggu hadapan.
Assalamualaikum and good afternoon. Welcome to iNuSTEC 2020. Okay, so for this afternoon session, we will start with session 6A. The theme for this afternoon session is science and engineering. Okay, I will be your chairperson for this evening. My name is Rogama binti Ramli. I'm from University Tenaga Nasional. So without further ado, okay, we would like to call upon our first presenter, which is Dr. Azhar Muhammad from Agency Nuclear Malaysia, with the research title Way Forward in Strengthening Mushroom Industry in Malaysia Through Nuclear Technology. Okay, so Dr. Azhar, the floor is yours now.
Okay, thank you, Mr. Chairman. I've heard my voice can be heard. Is it okay, everybody? So the title for my presentation today is Way Forward in Strengthening Mushroom Industry in Malaysia Through Nuclear Techniques. Actually, we know that the global mushroom cultivation market is projected to witness significant growth due to factors such as the multiple health benefits of mushrooms, increasing per capita mushroom consumption, cost-effective production, and rising demand for vegan and natural food in the diet, and increasing health-conscious population across the globe. So it means that we need to strengthen the industry to making sure that the sustainability of the industry in Malaysia. Next. So my content today is the first I will introduce about mushroom a bit, and then later on I go to the mushroom industries, and then I will share with all the audience about the nuclear technology in mushroom industry, and of course the final one is related to the way forward in this mushroom industry. Next. Okay, first of all, what is mushroom? A mushroom is a microfungus with a distinct fruiting body, which can be either epigenous or hypogenous, and large enough to be seen with the naked eyes and to be picked by hand. Actually, mushroom is under fungus. Yeah, the different only with the fruiting body. Next. So in Malaysia, we have two types of mushroom. The first is lowland mushroom, which are related to the temperature 24 to 38 degrees Celsius. And the second one is related to highland mushroom, 10 to 23 degrees Celsius. If you can see that the names there is a local name like tiram kelabu, tiram putih, tiram kuning, it's all under varieties. And the highlands related to enoki, shiitake, tiram raja is also local name. Shiitake is lantinus. And we can see that this is where we grow the mushroom. Next. And here I would like to share the pictures of mushroom in Malaysia. So what we can see that on the top with the red one is a local cultivated mushroom in Malaysia, and at the bottom on the left hand side is also local cultivated, but this one is meant for medicinal purposes. And if you can see that on the right hand side, the bottom one, this is the exotic mushroom, which only can found only in certain time only. And this mushroom cannot be cultivated. Next. What we can see here, before 2000, year 2000, mushroom is considered as low profile crop. 2000-2010, the mushroom becoming the potential crop. And after 2010, the mushroom becoming a high value crop. So what you can see that the demand of the mushroom is getting more and more, and that's why we need something to do with this mushroom so that the sustainable of the production can improve the mushroom industry in future. Next. The importance of the mushroom, we can see that the mushroom can be used as nutraceutical, as a food, and cosmeceutical, and also for pharmaceutical, and the final but not least is also used for biocompost. So in Malaysia, they have 4 main species. known as Pleurotus, Wolvarella, Schizophila, and Auricularia. The previous picture that I already showed you, if you can remember, is the total of the cultivated mushroom, and we focus now for the commercial is only for these 4 main species. So in Malaysia now currently is an adequate production to meet the market because the demand is very high. So means that we require a new cultivation method, and also we need a new strain or new breeds to fulfill the needs. And of course, the waste from the growing mushroom, we can convert it into bioenergy, fertilizer, and biocompost. And the easy way to say that the mushroom is a zero waste industry. Next. Okay. What we can see here is about the issue and the challenge. The first is related to the production itself, which is related to the mother culture, quality seedling, mass production, and downstream product. And the second one is related to the R&D, which is related to screening and selection, strain improvement, and also the research focus. The third is related to the technical support, which is support from government and also from the private company. And the last is a marketing. It's related to networking, campaign, and placement. All these things actually is integrated each other. But what we need is more than this actually as a core for the main sustainable mushroom in Malaysia. Next. Malaysia direction. What is our direction in mushroom? First is the diversity of the species, so that we can use many species to fulfill our needs. Second is related to the high-tech and systematic of the using of IoT, which is Internet of Things. Third is large-scale or high yield, because we know that we have less space, but we need to get more yield and very short period of growing mushroom. The fourth is variety of medicinal, cosmetic food product, and functional food. The number 5 is comprehensive waste consumption, because of course, if we grow mushroom, we have more waste and we need to manage this waste. And the final one is just to support all these things is related to the tourist production. Okay, next. In Malaysia, this is just what we call it to share with all of you the capacity mushroom house. For 20 times 24 feet, you can estimate 12,000 ringgit Malaysia, can utilize 5,000 blocks, and so on, the bottom. And in Malaysia, we have a scale for these mushroom growers. For the first one is less than 1,000, you call it hobby. The second one is small, more than 1,000, and the medium, and the big, and the corporate scale. Based on this thing, what I can say, most of the Malaysian growers is a small growers. Okay, next. This is the small growers look like how their hut, or what we call it, the mushroom house, the block less than 5,000, yeah? So you can harvest 1,000 blocks for every day. The yield is approximately less than 50 kilo per day. Next. This is the medium scale, a bit bigger, and a bit systematic. The blocks is approximately more than 5,000 and can harvest approximately 1,000 to 10,000 blocks per day. Next. This one is a big scale. Yeah? The big scale is not really common in our country. Why? Because the cost to build it is quite expensive. So people are not tends to go for this. But for the big growers, you can see that how many blocks they have and also how many kilograms that can sustain per day. Next, the main component of the mushroom industry, I can divide it into 5. The first related to tissue culture, second one is related to cultivation, the third is related to the product, the fourth is supplier, the fifth is the composting. The one that I rounded with the dot line is related to the where the nuclear application can suit in. It is related to the mutation induction in the tissue culture, decontamination in the product, and also in the composting, and sterilization can be used also into the product and the composting. Okay, next. Next. Okay, what is it? From in your mind, the first one is expression of the enzyme in the growing mycelium. The second one is a gamma put in the protecting gamma ray. These two things we will integrate to get something. Next. Gamma radiation in mushroom industry. By using the application of nuclear related to the gamma ray, we can create the new strain of the global environmental, which is robust with the global warming now. Strain variability for the selection, specificity mushroom for specific product, decontamination for dried mushroom and processed product, waste substrate sterilization for biocompost, and mutated microbes for degradation and bioremediation process. Okay, let's see what's the advantage of the radiation treatment. Next. So, the advantage of radiation treatment, the first is terminal processing, which is due to the penetration depth, meaning that they can go beyond. We can put the product in a box even, but still we can utilize the gamma ray. The second one is a cold method, or cold temperature independence. The temperature increase during the treatment are minimal, so it's good for our material, and it's chemical free and no residue. Next. Flexibility. Time efficiency, sterility assurance level, SAR, and ease. This is all the advantage of radiation treatment. Okay, next. But beyond this, there are the disadvantage of the radiation treatment. We have three here related to the instrumentation, which capital costs are high and specialized facilities are often needed, and the product degradation means that the radiation-based method are not compatible with all material and can cause breakdown of the packaging material. That's why we need to study first what and how to put the material in before start doing the radiation. And finally, the radiation material, which is where to put the things after we use it. I mean the waste of this material, the disposal. Okay, next. Okay, this is the radiation process for the mutation induction. I can show you here, we use the gamma radiation to improve the stream. If you can see that, left-hand side, how the device being used, and you can see also the devices together with this, and also the dose distribution. Okay, next. So actually, radiation mechanism on the living cell actually they damage the DNA or the genetics background of the strain, and due to the replication, the genetics become new one after the change, and we can have the new material or new strain which need to go for screening, and we can choose what sort of material that we need. Okay, next. This is another facility that we use for the activity of substrate sterilization and also the product decontamination. So you can see that the Radura logo there, before and after. Okay, next. This is the high quality control selection on how we select the strain after we do the irrigation. We introduce this procedure to growers, and also we use this procedure to get a good strain. From what we are doing so far, we have managed to get certain things that we are really good for the purpose of new breeds. Okay, next. Potential mushroom seedling after exposed to gamma radiation. So this is the result. Finally, we managed to get the new strains. The quality seedling comes from the quality selected mushroom strain, on which we use this thing to cultivate mushroom. You can see that the mushroom on the top is in the PDA, and on the left hand side, on the bottom, we use the liquid to grow the mushroom. And all these things we call it seedling for the mushroom cultivation. Okay, next. So this is the dried mushroom product from gamma radiation. This is the mushroom after we dry. Of course, the dried mushroom cannot last longer. We need to go for radiation, making sure to decontamination this dried material so that but not all the biohazard microbes can be removed totally. Okay, next. At Nuclear Malaysia, and specific to Agro-Technology and Bioscience Division, our contribution to mushroom industry is related to 3 strains. The first is Wolvarella, the second one is Pleurotus florida, is a white one, and the last one is Pleurotus pulmonarius. What we do, we just do the mutagenesis process. We help people with the mutation induction, tissue culture moleculars, and also for the commercial, we help the cultivation, we transfer the technology, the practices, and also we do the product radiation. And of course, all these things also related to the project community, because the cost for handling the mushroom farm is not expensive, and also for the products, it's not so difficult to do. That's why this project is very suitable for the community projects. Next. Why I can say that in vitro propagation after acute gamma radiation is good? Because it's a good process, rapid, reproducibility, easy to handle, and also can be used as a storage. And for the industrial benefits, for example, like producing enzyme degradation abilities is very, very important, because in fungus or mushroom, we have loads there to extract for the industrial use. And another one is for research benefit. The benefit is many, because we can manipulate the genes there by radiation, and also we can exchange the resources by using these techniques in vitro. Okay, next. All right, it comes towards the end. The presentation is to provide an understanding, actually, for the propagation perspective, advances, evidence, and challenge in nuclear technology for edible mushroom improvement in sustaining mushroom industry in Malaysia. So we do hope that all the things that I shared with you today can be a way forward in strengthening the mushroom industry. With that, thank you.
Okay, thank you, Dr. Azhar, for your presentations. Okay, next, I will call upon Puan Hazwani Muhammad Faizul. Okay. With the research title, okay, determining the effects of polydyne settling vesicles against gamma radiation. Okay, Puan Hazwani, the floor is yours now.
Assalamualaikum and good evening, everyone. I am Shadmani from University Technology Malaysia today. I would like to present my presentation slide, which titled the determining the effect of polydiestylene in stress against gamma radiation. So next. Okay. So for the research objective is to determine the effect of polydiestylene PCBA vesicles at different radiation doses. The materials that we are using are pentacosylanic acid and also the chloroform. Next. Okay, so for the introduction, nowadays radiation is important for improving the quality of consumers' products such as food, polymers, and electronic devices. So, to differentiate between irradiate and unirradiate products, the radiation indicator was introduced. Radiation indicator labels diaphragms are indicated in indicate the presence of irradiate and unirradiate products by referring the color changing. So the color of the indicator change based on the exhibit dose when the indicator will irradiate with gamma rays. So the conjugated polymers causes adverse advantages toward inorganic materials and small molecules, organic materials, such as lightweight, lightness, and flexibility. So for the examples for the polydiestyrene, the examples for the conjugated polymers are polydiestyrene. So the next is okay, so polydiestyrene PCDA or 10-12-pentacosadienic acid is a conjugated monomer known for its optical shift following the exposure to radiation. The PCDA polymer is formed via chemical polymerization, where the diestyrene molecules are pre-organized in the molecular acid wise with the C1 and C4 carbons of lead monomers purposely placed in the closest distance to facilitate one-time polymerization. And then the preparation of the polymers and PCDA will be followed up via two-film hydration method. So this is the molecular structure of 10-pentacosadienic acid PCDA. And the next is the sample preparations. First of all, we measure the 10-12-pentacosadienic acid to 0.025 gram and then dissolve in 10 ml of chloroform, and then the solution was done using a liquor. The next is the 20 ml of distilled water was added to a liquid concentration of 1 millimole. Then the sanitation process will perform until the homogeneous liquid form. And after that, the solution was filtered using the filter. Next. The next after we filter, we radiate using the gamma radiation. So this is the irradiation of the PCDA vesicles using gamma radiation. First of all, the PCDA monomer vesicle solution will subjected to various doses of gamma radiation in order to get the polarized PCDA vesicles. And then the PCDA vesicle solution was divided into 5 doses of gamma radiation, which is first 1 gray, 500 gray, 1000 gray, 3000 gray, and then 5000 gray. So this is the samples of the PCDA monomer vesicles before review. Next. Okay. So this is the polarized PCDA vesicles after review. As you can see, the 400 1003, 2003, and 5003. After gamma radiation, polarized PCDA vesicles show the changes of the color from the colorless to the blue color. These are the samples above. You can see that the color changes at 2003 and 5003. Okay, next. The changes of color occur because of the colorimetric properties of PCDA vesicles. So this is the color changes of polymerized PCDA vesicle. The polymerized PCDA vesicles is formed by the chemical polymerization, which is C1 and C4 carbon of neighboring monomers previously placed in the closest distance to facilitate the 1,4 addition of diverse monomers. The result is an intensely colored polymer, particularly of a deep blue color. Next, this is the examples of the particular polymerization of PCDA vesicles. And after that, we go to the result of the discussion. So first of all, for the dynamic discussion, which is DLS, from the graph, you can see that increase data, the size of the particles will increase when the radiation is increased. As you can see, this is the radiation dose, and the highest is the 5000 K. Okay. The electricity used to determine the size of the electricity in the millimeters first. The initial dynamic electricity results demonstrate that the electricity inverse disrupt the formation of the resistance. The radiation dose of the electricity was affected by the color changing of the samples from white to dark blue. And then the blue color was started to form at 2003. The color intensity was related to the observed dose of the radiation. In general, the higher the dose, the more intense the blue color observed on the sample. You can see that from the graph, the increase of the size of the particles, the radiation dose of the PCBA also increase. So for the hypothetically, the smaller the size of the molecules, the faster they can move. Next is the UV spectroscopy. So here you can see that from the spectrum, you can see that the highest peak is about 640 nanometer each radiation dose. And the highest one is 5003 at radiation dose. The UV spectroscopy is to analyze the absorption spectrum of PCBA before the 15 nanometer. Then the effect of ionizing radiation on PCBA was measured by using UV spectroscopy for the absorbing spectrum corresponding to the absorbing dose up to 500 up to 5003. The maximum absorbance at the wavelength 650 nanometer was chosen, and it is indicated that the visibility properties for the blue color of the PCBA. From the results, 640 nanometer band showed a slight improvement with the increase of the absorbed dose of the dose at 5000 is the highest peak compared to other radiation dose. Indirectly, the free radicals that they formed reacted with the PCBA and slightly contributed to the formation of the hydrogen and volume interest of the PCBA. With the highest absorbed dose, which is at 5000 Gray, the absorption band increase. The absorption band increase at 640 nanometer due to the disorder defect in the amorphous nature in the polymer chain of PCBA. Hence, so it involves more degradation and dispersion of the PCBA. And for the conclusion, yes, first of all, the PCBA resistance has combinated properties with gamma properties when irradiate with gamma rays. Then the color changes at radiation dose of 2000 Gray and 4000 Gray when irradiate from colorless to blue. And the dynamic light spectrum results show that increase the size of the particles, the radiation dose of the PCBA also increased. And the maximum absorbance, 640 nanometer band, showed a slight improvement with the increase of the absorbed dose while UV spectroscopy. So this is the conclusion. And then next, reference, and I think that's all from me.
Okay, thank you, Puan Hazwani, for your presentation. Then we will continue with our third presenter, which is Associate Professor Dr. Nasri from Unit 10 with the research title Applications of Neutron Clouds from Puspati Trigger Marks II, Research Director in Enhancing Superconducting Properties of BSCCO Superconductor. Okay, Dr. Nasri, the floor is yours now.
Assalamualaikum warahmatullahi wabarakatuh and very good afternoon. Thank you, Madam Rogama, for the introduction. I'm Nasri and Zahida is my co-researcher. Most of the work that we conducted actually done with collaboration with Malaysian Nuclear Agency, Nuclear Malaysia. I'm very thankful to all their staff and researcher officer over there who really support our research work. So as you can see, the title is the application of neutron flux from Puspati Trigger Mark II Research Reactor in enhancing superconducting properties of BISCO superconductor. So next. Okay, the outline of our presentation will be as usual. There will be a little bit background and then the objective of our research, methodology, result and discussion, and at the end, the conclusion. Next. Okay, a little bit about the superconductor. So one of the two parameters, there are many parameters actually, two of the important parameters for superconductor to be applied in application in devices are the transition temperature and also the transport critical current density. So basically, the transition temperature is the temperature in which the superconductor will transform into from normal state to the superconducting state. And in order for the superconductor to be applied and in order for us to enhance the properties of the superconductor in terms of their transition temperature and also the transport current density, we need to have a very good flux pinning capability within the grain of the superconductor. So from our past experience, we have actually did some work. For example, we add nano-sized MgO particle, and also we did some radiation with using neutron on our material or our superconductor, and we found that there will be some enhancement in terms of their TC and JC. So it is most likely due to the formation of defect that will actually become the pinning center for the material to be highly capable and able to have a very good what we call the transition temperature and also the critical current density. Next. So in the more or less what I have mentioned earlier in the introduction, in order for the superconductor to be applicable, so there must be the superconductor must be able to sustain the transition temperature and also the current density in various circumstances, and especially in the environment if there is irradiation. So our research is mainly to focus on how we can improve the TC and the JC, the transition temperature and the critical current density by looking or by improving the texture of the material. So what we mean here is that we try to develop a texture where using radiation we are able to create a defect, and this defect eventually will become the flux pinning center for us to have a sustainable transition temperature and critical current density of the material. Okay, next. Okay, we have a few objectives in our research here. Firstly, we wanted, of course, to see the effect of neutron irradiation on the two superconducting properties that I mentioned, the TC and JC. And also we wanted to look into the microstructure of the material, whether with the irradiation by neutron, we are able to have a good microstructure and high texturing coefficient. And also we wanted to see, this is part of the research as well, if we add little bit nano-size MgO, so we use MgO because the magnesium particle won't be reacting with the main component of the superconductor. So the reason the addition of MgO is basically just to create more defect within the superconductor grains. And also we wanted to see what are the composition of the superconductor, because we are using BISCO. BISCO means you have bismuth, strontium, calcium and copper oxide together. So we wanted to see which part of the material will actually contribute to the radioactivity once it is being irradiated with a neutron. Next. Okay, the methodology is quite simple. I think everybody are familiar with is familiar with the method. We are using the conventional solid state method. So the purity of all our chemicals is very high, more than 99.99%, and we the sample undergoes the heat treatment, and eventually we pelletize those into small discs of diameter about 30 millimeter, thickness about a few millimeter, maybe 2 to 3 millimeter. So as you can, as we know, the reason why we use this solid state method basically is very convenient. We don't need to use any solvent, and when we do the characterization, we can actually reduce the formation of impurity phases in our sample. So next. Okay, over here, this is how the flow chart of our process in doing the research work in gathering the data individually to analyze our data. So as I mentioned, we prepared the sample using solid state reaction method, and then we use the neutron flux from the trigger Puspati for the flux is about 2 times 10 power 11 neutrons per centimeter square, and we expose our sample for 6 hours to get the total fluence of 4.32 times 10 power 15 neutrons per cm square. So from the sample, we did the testing. So first using the cryogenic 4-point probe, in which we reduced the temperature of our sample until it reached the transition temperature. So it's about, I think, slightly above the liquid nitrogen temperature, about 80 Kelvin. And then we did the scanning electron microscopy to observe and analyze the microstructure, and then eventually we look into the structure, the alignment, and the grain boundaries of our sample. Okay, next. As you can see in the table here, so these are the elements that we use in our superconductor. We have bismuth, strontium, calcium, copper, and also further oxygen. So as you can see, we use the WISE uranium project calculator to figure out the activity and also the half-life. So we found that the copper 63 is the one that contributed to the radioactivity in our sample once we expose our sample to the neutron. So the radioactivity is about 12.76 millicurie. So that's why it's very also for the researchers very important in handling the superconductor. So we need to use the proper handling as a protection to avoid any health issues with regard to the exposure to the radioactivity. Next. All right, over here you can see the result of the transition temperature, the TC, and also the JC is the critical current density. So you can see a very good improvement with once the sample are irradiated by neutron. The only thing that may be a little bit, it's not that much actually. If you compare the transition temperature at zero transition temperature, that means when the sample start to become superconducting, there will be a little bit increase in the zero TC. That means the value is a little bit reduced, but the another aspect that we need to look into will be the gap between the TC0 and also the TC onset. So we found that for the irradiated sample, the gap between the TC0 and the TC onset is quite huge. So we will discuss about it in the next slide. But the most thing that the thing that we discovered in our research is that there is almost 5 times increment in terms of the transport current density, and this is a very good value because the enhancement really happened after the sample are exposed to the neutron flux. Okay, next. Okay, looking at the SEM results, so if you compare between A and B, so the left-hand side is without irradiation, the right-hand side is the irradiated sample. You can see that in the irradiated sample, the orientation, the grain orientation is quite random, and the degree of texture is also quite high compared to the non-irradiated. But however, we found that even though logically the random sample supposed to have a degrading effect on the superconductor properties, but somehow we found that there will be enhancement in the JC and also a little bit on the TC. Okay, next. Okay, what we can say is that from the result and from our TC measurement, the JC measurement, and also the SEM, we found that the nuclear radiation, such as neutron flux, is able to create defects in the microstructure, but this defect is actually a positive defect because it becomes the pinning center for our superconductor to sustain its superconducting behavior. Okay, then the reduction here, what we mean is actually the gap between TC onset and the TC0 is due to the disorientation of the grain boundaries that is related to, based on other researcher, it is due to the oxygen vacancy in the CuO2 plane. Okay, in the superconductor, CuO2 plane is the one that is responsible for the current transport inside the material. and there are also multiple lattice distortion around the grain and the grain boundaries. And as we can see, the critical current and also the JC, which is the critical current density, we found that it enhanced due to the formation of extended defect. So this defect basically act as the effective pinning center for the material. So this will be significant in order for the enhancement of the IC and also JC. So back to the SAM diagram, as you observed just now, the sample that was being exposed to neutron radiation, basically more random and very disorganized, but on the opposite end, you can find better result in terms of their JC. So this is, we believe, due to the existence of strongly linked network of percollective path that combine with the interplanar coupling inside or between the components or the element inside our superconductor. So this contributed to higher JC, which was actually 5 times more than the one without any radiation. Okay, next. I think is the conclusion. So in this study, the neutron flux has shown to improve the superconductor properties, and in the research we use neutron fluence of 4.32 times 10 power 15 neutron per cm square. And then the neutron flux promotes the formation of uniform distribution or defect in the superconductor. So this initiates the formation of holes, which is responsible for the enhancement of the critical current and also the critical current density. And lastly, we saw that the neutron irradiation is in future, if let's say we wanted to use the superconductor for application in let's say radiation environment, so it is proven that the existence of neutron irradiation and maybe other radiation as well won't actually affect the properties of the superconductor. I think with that I end my presentation. Thank you very much for your attention. Thank you.
Thank you very much to Dr. Nasri for your very interesting presentations. Then we will continue with our next presenter, which is Mr. Jubaidul Islam. He will be presenting the research title, Density Distributions Investigation through the Geometrical Structure for the 27S hollow nucleus. Dear Mr. Jubaidul, the floor is yours now.
Thank you. Good afternoon, everybody. Actually, I am Jubaidul Islam and currently studying in Masters of Science in Nuclear Science program at the University of Kebangsaan, Malaysia. So, my presentation topics is density distribution investigation through the geometrical structure for the sulfur-27 hollow nucleus. And please next slide. These are the contents that I am going to represent for these slides. So please next slide. Okay, introduction. Actually, in this study, we have treated the sulfur-27 nucleus as a bromine nuclei with the configuration of core plus 2 valence proton configuration. In 1996, sulfur-27 nucleus was debanded as a proton halo. After that, in another study, it was confirmed that sulfur-27 nucleus is a proton halo for being a huge, big mean square radius of for the 2s state for the 2 valence proton. For this halo candidature of that sulfur-27 nucleus, we have investigated this nucleus using the Gaussian density distributions theoretically, applying the model geometrical structure. Please, next slide. Okay. For this study, we have focused 3 topics for this nucleus. Those are the nuclear core density calculations, the nucleus halo density calculations, and last one is nuclear matter density calculations. For these 3 density calculations, we have used the Gaussian density distributions because when the proton and neutrons stay in a nucleus, the nucleus distributions follow the Gaussian distributions. That's why we have investigated this bromine nucleus using the Gaussian distributions. Please, literature review. Basically, in 1995 and after in another study in 1996, Rent et al. Has investigated this nucleus to confirm that sulfur-27 nucleus is a halo nucleus for the valence neutrons in the state of 2s state. Please, next slide. Okay, after one decade later, the halo nucleus, especially for 2 neutron halo nucleus, that is one kind of that is also a bromine nucleus, helium-6, has investigated the different types of matters. For example, matter radius, core radius, halo radius, distance between the center of mass and the 3 body of the 3 body systems, and the valence to protons distance, and others distance of the coming from the geometrical structure. All parameters have investigated for the helium-6 2 neutron, considering the 2 neutron halo nucleus, and they have proven that it is excellently agree with the experimental data for the helium-6, especially for that 2 when the helium-6 is considered as a 2 neutron halo nucleus. Later on, especially in this year, me and my co-researchers have we have investigated this nucleus because still now we are waiting for the experimental proof that sulfur-27 is a halo nucleus. That's how we have investigated in the previous time, and we have our investigations has been published in this year, and we have shown that the sulfur-27 nucleus sometimes we have as a single proton halo nucleus and sometimes 2 proton halo nucleus. Though there are 2 proton halo nucleus exist the valence outer shell of the nucleus in the nucleus for the nucleus. So it is still now awaiting for the experimental evidence that whether the sulfur-27 nucleus is a single proton halo nucleus or two-proton halonucleus. Because in the same time, sometimes this nucleus behaves as a single proton halonucleus, and sometimes it behaves two-proton nucleus. Because theoretically it is correct, but still we are not sure that sulfur 27 we have a nature of duality. Because theoretically we have shown that the single proton, if we consider this a single proton halonucleus, still it shows that low separation energy. If we consider this two proton halonucleus, it also shows that still the nucleus is two proton halonucleus. Interesting matter is, for both of these cases, the low energy separation energy for the proton, for the two valence protons, still remain below the 2 million electron volt, in the range of 1.377 to 1.87 million electron volt. That means in our previous study, it shows the valence protons, two protons are still now loosely bound with its core nucleus. That's why we are investigating again this nucleus in other models, especially the Gaussian distribution, so that the nucleons, how the nucleons are distributed in the nucleus and the valence band or the outer shell of the nucleons in the nucleus. That is the main purpose of this our present study. Please, next slide. Model. So to do this, for this our investigations, we have considered this core of the sulfur 27 nucleus as a cluster core model. That means in the all protons and neutrons, that means all nucleons except the two valence protons, behaves like a single, they are clustered in the core and behave as a single body. If we consider this as a single body, then this cluster core and two valence protons form a three-body system. If it is true, then actually our calculations becomes a complex, more and more complex. We cannot apply that directly the two-body solution Schrödinger equations in quantum mechanics or classical mechanics. Then we have to solve the three-body or many-body system. To avoid this complexity, we have focused the interesting model, the geometrical structure that have been studied in the previous study in Renter et al. In 2015. However, we have considered the core of this sulfur 27 nucleus as a cluster, and following this model, we have applied the geometrical structure to calculate the geometrical parameters to investigate the core densities, halo densities, and nuclear matter densities for the sulfur 27. However, from the geometrical model, the calculated parameters have been used for the Gaussian distributions, because I have said in the previous slides that all nucleons, when they stay in the nucleus, actually they follow the Gaussian distributions, especially the density properties. That's why we have used the Gaussian distributions. But to investigate these distributions, we have calculated all parameters from the geometrical model. Please, next slide. This is the geometrical structure. Considering the three-body system, where the core is considered as a cluster core for the sulfur 27 halonucleus. In this figure, the blue boundaries and shaded circle shows the core nucleus. That is actually comes from when we consider when we deduct the two valence protons. That means we get the silicon-25 nucleus. We have considered this nucleus as a core nucleus. When we consider this nucleus in the sulfur-27, then we have to add the two valence protons to get the sulfur-27 nucleus. So we can see that the valence two protons are presented in the yellow color, that is P1 and P2. And the silicon-27 that has been considered as a core nucleus of the sulfur-27, that is represented by shaded and boundaries by blue color. Then the figure shows that there is a three indivisible body or particle. When this three body systems is applied, the geometrical gives us the center of mass system, and the core, it has itself a center of mass, center of core. So the center of core of the nucleus and the center of mass of the three body systems, these are two difference points. So we have to calculate the distance between the center of core nucleus and the center of mass, that is indicated in cm in the figure. So, and RSM, that means lowercase rsm, it is represented the RMS matter radius of the core nucleus. Basically, using these two parameters, we have calculated the core nucleus of the sulfur, and this core radius of the sulfur nucleus is represented in RC by the RC, and RM represented the capital RM represented the RMS matter radius of the sulfur-27, and so on, and different types of others. And R is indicated, that is the distance from the center of mass, and the red color circle, this distance is actually RMS halo radius. These two variables actually used in the Gaussian distributions. And to calculate these distributions, others parameters have to count first, then we can get the RS and RC, that means core RMS core radius of the sulfur-27 and the RMS, that means root mean square radius, halo radius of the sulfur-27s. Please, next slide. Okay, from consider the above geometrical structure, we have to follow the equations 1, 2, 3, 4. First, we have to calculate the equations using the equations 1, the distance between the center of core nucleus and the center of mass of the three body systems. Using this, after getting this parameter, we have to apply the other parameters, for example, RMS core radius and other parameters from the figure 1. Please, next slide. Next slide. Okay. After this, from the equation 2, we have seen that we can easily get the RMS core radius of the sulfur-27, and applying from the same model or geometrical structure, we can get the equation using the equation other parameters, especially for distance between the two valence photon distance and the halo radius using the equation 5 and 6. Basically, we have used the equation 2 and 5 inserting into equations 7 and 8. Equation 7 indicates the core and halo density distributions, and 8 indicates the RMS nuclear matter density distributions. Actually, we have used equation 2, 5, 7, and 8. Okay, please, next slide. Okay. to draw and after calculations the all parameters, we have just investigated these three densities applying the MATLAB software, and we have just told that equation 2 and 5 we have inserted in equation 7 for the halo density and core density measurement, and equation 8 is used for the nuclear matter density distributions. Please, next. Okay, this is our from the geometrical structure that our calculated geometrical parameters for the study of the Gaussian distributions for the sulfur 27 halo nucleus. Here is the presented in the table. As here is, we can see that Rs, that means core radius of the sulfur 27 is 3.163 centimeter, and especially the halo radius is 4.0994 centimeter for these configurations, not all others configurations, when we consider the nucleus as a two proton halo nucleus. Okay, please, next slide. Using these parameters and using equations 7 and 8, applying the MATLAB softwares, we have plotted the three densities, that means that are shown in figure 2. The blue color shows the core density, red color shows the nuclear matter halo density, and green color shows the matter density, nuclear matter density. From the figure, we can see that the core density is maximum among of these three density distributions when the nucleons are it is shown at the center of the nucleus, but at the same time we can see that the halo radius density is minimum lowest value among these three distributions, but though the halo density is lowest value at the center of mass, but the tail of this halo density is longer than other two core and matter density distributions. This is the interesting result. Okay, please, next slide. Okay, we can conclude from this figure that we can say almost all nucleons are distributed in the core of the nucleus, and the core density is maximum among the core, halo, and matter density, because all nucleons except the valence protons are considered as at the center of the nucleus. It is true from the figure. And third, tail of the halo density is larger than core and matter density. Since valence protons are staying far away from the core, that's why the tail of the halo density is longer than the other two distributions. These halo distributions indicate the protons are distributed in the larger radius of the nucleus and exist outside of the core of the nucleus. For larger tail, distribution shows that sulfur graphically shows that, and theoretically, when we consider the geometrical structure for this bromine nucleus, especially when we consider these two proton halo systems, then the sulfur 27 is still now theoretically that proton halo nucleus, especially we can see that two proton halo nucleus. But we are still now waiting for the experimental evidence. So that is important and crucial, but we are now still predicting this, the nucleus as a proton halo nucleus or proton halo nucleus theoretically, but we are not sure. We have to wait the future upcoming experimental evidence. After that, we can say without any doubt, but theoretically it's true. Okay, please, next slide. And this is the reference all. And please, next. Oh, and last one is to carry out these investigations. We thank the University of Kajang for the grant, GGP 2017-003. Okay, please next slide. Okay, thank you very much, everyone. If you have any questions, please you can.
Okay, so thank you, Mr. Jubaidul Islam, for your presentations. Now we move to our next presenter, which is Mr. Leo Kiwa from Agency Nuclear Malaysia. Okay, with the research title, Study the Dose Profiles of the Low Energy Electron Accelerator, LEEA. Mr. Liu, the floor is yours now.
Very good afternoon, everybody. So my name is and today I think this is the wrong PowerPoint. This is my post. So can the PowerPoint right? I think this is wrong. This is for the poster system. Can you hear me? Hello? Hello? This hello, can you hear me? Hello? Hello? Can you hear me? Hello? Hello? Okay, my name is Leo Rukiwa. I'm from Malaysian Nuclear Agency. Actually, this words being study the competitive correlation for the compact hadron driver for the cancer therapy driver accelerator. Is the correlation works with high energy physics, high energy accelerator organization from Japan. So my collaborators Professor Takayama, Atachi, Kawakubo, and Dr. Tanuja from India. Next slide. So this is the content of my talk. So the first I will cover the driver of the lattice parameter. Then I will show you the driver system. Then the correlation of the competitivity, which the definition of the competitivity. Then what kind of the method for the correlation. Then I will move to the I think the result, the discussion, and the conclusion. Next slide, please. So this is the lattice. I will go for the lattice design. And next. So for this lattice for a ring, so we had this is the lattice is the we call it the mirror symmetric lattice. So the configuration is the shell A. You can see in the slide, shell A is composed of the. You can see it's the focusing is the drift space. Focusing drift space is the bending magnet. Then the focusing with the drift space again. Then bending magnet, drift space again, focusing magnet, and the drift space. So the shell B also the same configuration, but the strength is the different. So that means the parameter of the focusing and the focusing components for the shell A and shell B is different. So the configuration of the ring is the half ring with the shell A, B, drift space, B and A. So this is the parameter. We had the D1 until D4 is the drift space for the for this shell A and shell B. For the quadrupole magnet for the K value and the length. So it's these the parameters that we have. Also the bending magnet. So next slide. So we can see this the hadron driver parameter. So for this driver, we design the lattice. We require lattice for this design. We had a dispersion free region. Also, we have the large dispersion region. So the free dispersion region, we will allocate the. You can see the induction shell and the sun kicker in here. The injection kicker, injection coil or injection device here, and the induction shell will be placed also in this free dispersion region. For the large dispersion region, we will allocate the extraction device at the kicker inside this region. So this is the parameter that we have. The energy is the 200 mega electron volts per nucleon. So this is you can see the parameter in this table. So you can see the half ring consists of the shell A, B, drift space B, A. So it's the mirror symmetric lattice. So the other side they have the same parameter. Or say we will have the same we call it the switch parameter or the current strider parameters. So next slide. Okay, this is the lattice we have. You can see the color. Because in the slide here I couldn't see the color very clear. So you can see the horizontal beta function, the vertical beta function, and the white in the red is the dispersion free region. So as I mentioned that we have in the middle you can see the dispersion region is the free dispersion region. So you can see is most zero. So for the end, for the both edge, you can see is the large dispersion region. So this is the required parameters for our design. So for one purpose is we want to extract the beam. according to the momentum deviation in the dispersion rush dispersion region, and also we are trying to avoid the momentum deviation inside the induction shell or the inside the injection kicker. So next slide. Sorry, go back to the previous slide. Sorry. So you can see in this figure, this graph. So it's the ideal case. So when in this one, we assume that this is the ideal particle that we have. So we don't have any momentum deviation. So they say we are required the 200 mega electron per nucleon. So this is the energy of each particle they have. But in actual case, each individual particle, the beam will consist of the many particles. So each particles might have the different energy, is mean the different velocity. So they had some momentum deviation. I try to study some perturbation were caused by the we call it the beta tone tune. So it's will cause the some perturbation that we call it the chromaticity. So next slide. So this one we are trying to I will try to show you some correlation for the chromaticity. So next slide. Okay, you can see this the definition of the chromaticity. So we can define the radiation of the tune, beta tone tune is the transverse beta tone tune, of course. So related to the momentum deviation. So this is the definition. So for the formula below here is the second one. Is the natural chromaticity of the caused by the focusing or diffusing quadrupole. So you can see it's the K value, it depends on the K value. Also depend on the beta function or one the trace parameter. So you can see in this figure. So for the particle with the ideal particle, they will focus in the ideal point. But with the momentum deviation, they are with the momentum deviation largest or the smaller, they might have a different focusing point. So this effect will be caused by the tune or the beam that we call it the beta tone tune. So in accelerator physics, the tune is defined as the number of the beta tone oscillation inside the one revolution or the circular ring or the circular accelerator. So next slide. So you can see. So actually, this the oscillation of the beam inside the ring can be explained by this pendulum figure. You can see. So they will start for some point. They were moving back to the initial point. So this is the same in the ring of the oscillator, but of course this is the ideal case. But in the actual case, we have the oscillation on the beam. So the beam might not be the circulate inside the circle way. Okay, so for the right hand side of your right hand side of the figure, you can see the perturbation formula here. You can see we had some assumption for the momentum deviation 0.01. So we had some chromaticity number. So this case happen. So for each term, when the beam come here, they will have a kick here for first turn, second, third, and fourth turn. So you can see they were moving up. The beam side will be largest. So finally the beam will be kicked off or out from the ring. So couldn't be focused. So it's this the reason why the chromaticity correction is required. So next. Okay, so we are required to correct the complexity, but by which kind of the component or the method that they could be done. So in here, typically, what are the component can be compensate the complexities is the searchable manage. So in this case, the correction complexity of the searchable manage is expressed in here. So the G here is corresponding to the strength of the quadrupole, and this then some the N here is corresponding to the dispersion function, and this is the beta S. So we have the as I mentioned that we are trying to correct the beam inside the transverse direction. That means for the vertical and the horizontal directions. So for we have the S and Y. So next please. Okay, this is the correlation for this driver. Next please. Okay, there you can see. Summary all the formulation in here. This one slide. So the first is the natural complexity. It is for we have the S and Y directions here for the expression one, and so we are trying to introduce this correlation to compensate this natural complexity. So this we are trying to get the G number for the X searchable, S direction searchable, and it's a horizontal, and for the vertical searchable. So according to this formulation, we are trying to find the best configuration. How many searchable minutes are required, and what is the strength of the minute. So in which location we should locate the minute in which location, which is the best location inside the ring. Okay, next slide. Okay, this is the case A. So for this case, we just assume that we had two searchable. So in the searchable length is the 0.2 is the base. Basically, this is the length of the searchable. So this is from the initial point here to here. So we are trying to get the field strength of the searchable. So next slide. So you can see we have the two searchable here in this equation and this location. So next slide, please. Okay. So for this the formulation, so we are trying to get the G. So this the numbering or the parameter that we got it on this formulation. So it's the 28 point something and then minus 38 point something. So next slide. So you can see the ideal case in the natural complexity is caused by the sorry, I forgot to mention that in this case the momentum deviation that we are assumed that is the 0.01, because this figure that we got from the experiment for the current machine of the KEK, the KEK digital accelerator. So they had the experimental data and the simulation data. So they have the momentum deviation of their beam for the 0.01. So you can see for the ideal case with the material complexity after the correction. So after the correction, the ideal case after the correction is the overlap. So we couldn't see the clear picture here because there's overlap. So that means the figure, the number that we got is for the G1 and G2 is 28%. 38%. We can compensate the natural complexity. Okay, next slide. So next slide, please. Next slide, please. Okay, this for the case B. So in the case B, we assume that we had a 4 searchable in this location. So we are trying to find the G1 and G2. Some both are 1, 3 have the same strange and located at the position with the same Coulomb slider. They mean the beta function is the same. So the 2 and 4 also have the same location and the strange. So okay, next slide. You can see the location for this one. So that we had a 1, 2, 3, 4. So now we are trying to with the G1 and G2. So next slide, please. Okay, so this is the result that we got. There's a 14 point something, and another is the negative 19 point something. So you can see when we increase the number of research pool, the strength will be reduced. So it's quite reasonable. So next slide, please. So this is the result that we have after the composition and before with the ideal case. So next slide, please. So next slide, please. Okay, this KC. So KC also we have same assumption as the case B. We had the same range of the sample 1 and 3. Also the sample 2 and 4 also had the same G number, the range of number. But we are trying to select the location. We have the different that for the case B. Next slide, please. So you can see this location that we are trying to locate our sample here. So next slide, please. Okay, you can see although the number of the sample are the same as the case B, in this case C, but you can see the required strength is reduced drastically. You can see. So next slide. So this just the result is the same. Okay, next slide. Okay, next slide. This expression region. Okay, you can see that for A, B, C. So the type of research pool we have 222 for 3 cases. So the number of the research pool is the BC is the same. Then A is much much a bit smaller. We have only 2 numbers. So but you can see the important parameter that we are trying to get is the G1 and G2. So next slide. Okay, you can see the conclusion. So for the natural competitive composition, so we is very dependent on the Coulomb slider parameter. So also we know that for the case A and B, so when increase the research pool number, so the strength of the research pool will be reduced. So the location or the where to put the research pool magnet, we had to choose according to the Coulomb slider parameter. So as I show you that for the case B and case C, we have the same number of the magnets or the sample magnets, but the strength of the sample magnets is very quite different because the Coulomb slider parameter for the location case B and case C is different. So for the location for the case C, we choose the largest Coulomb slider parameter. But case B, we just simply put inside some location, maybe with a smaller Coulomb slider parameter. So you can see the difference. So we can, from this result, case A, B, C, so we are selected the case C is the required number. So sorry, this some type area is the case C is the best solution. So next slide. Okay, that's all. Thank you for your attention. So any question?
Okay, thank you, Mr. Liu, for your presentations. Okay, now we will move to our next presenter, which is Mr. Ng Yen, with the research title, Theranostic Applications of Lutetium-177 Level Peptides, First Experience in Radio Labelings and Stability Study. Mr. Ng, the floor is yours now.
Can you hear me? All right. So I can start now, right? Thank you, Madam Chairman, Madam Rashma Ramdi. Good afternoon, everyone. I'm very delightful to be here to present one of my research topic. The topics of today is the theranostic applications of lutetium-177 label peptide. This is the first experience in the radiolabeling and stability study. And below is my team member from Agency Nuclear Malaysia. Next slide, please. This is going to be the contents of my presentation, including introduction, objective, some method, results and discussion, conclusions, references, and acknowledgement. Next, please. The receptor targeted radiotherapy using specific peptides has been used clinically for the treatment of a number of solid malignancy tumors. Peptides are short-chain acid amino, and these peptides offer many advantages, including increased permeability, low toxicity, and they are easy to prepare as compared to some others biological compound like monoclonal antibody. This peptide we can synthesize once we get the right structure. Peptide radiolabel with lutetium-177 is an very exciting new development in the field of radionuclide therapy. Next, please. So what is lutetium-177? Lutetium-177 is a reactor-produced radionuclide. During the decay, the lutetium-177 emits beta radiation, and this beta radiation is very useful in killing the cancer cells. So once we deliver this lutetium-177 into the cancer cells, the beta radiation is able to kill the cancer cells. And it has a half-life of 6.67 days. Not only the beta radiation, during the decay process, this lutetium-177 also emits gamma photons. Candidates in the theranostic application. Theranostic means therapy and imaging. With one isotope, we can make two studies. Next, please. The model peptide used in this research is the DOTANOX. DOTANOX peptide specifically bind SST receptor subtype 2, 3, and 5, which show overexpression in neuroendocrine tumors. What is a neuroendocrine tumors? This tumor, usually we call NET, are cancers that begin in specialized cells called neuroendocrine cells. These cells are similar to those of nerve cells and hormone-producing cells. These NET tumors are rare and can occur in anywhere in the body. There are many types of NET cancers. However, these cancers most commonly arise in the digestive tract, such as and also the lungs, appendix, pancreas. They can also grow in the lymph nodes, brains, even in the skin. So the treatment for this NET remains a big challenge in clinic. It is because normally it is in the early stage of this cancer, it is quite difficult to detect. And also, they are also called silent killer because once it is detected, normally already in the late stages. And the survival rates of these patients are quite low. Therefore, specific targeted therapy using the specific receptor agent such as a peptide is highly recommended. Due to the difficulties in the detection and treatment, lots of efforts has been done in the developing of new and promising drugs, especially to realize the personalized medicine. So there are several peptides that target these NETs, such as dotanol, dotatate, and etc. So in this study, we use the dotanol. And labeling with lutetium-177 is presently being considered as one of the most promising radiopharmaceuticals for the treatment of these types of cancer. Next, please. Next slide, please. An example shown here is a study done in India that is published in this Journal of Gastrointestinal Oncology that used the gallium-68 dotanol as an imaging. Previously, sorry. This one, as you can see in this picture, clearly showed that where is the origin of the tumor, which is very useful in the planning of the treatment. Next, please. Next slide. So the objectives of this study include to develop a lutetium-177 peptide labeling protocol in our lab to evaluate the stability levels and to investigate in vivo peptides. I would like to emphasize here, this is the very beginning of this study because in our agency, we just begin to start to produce this lutetium-177. So we would like to test on the skill of our labeling using this lutetium-177. Next, please. So the production of lutetium-177 was produced by irradiation of enriched lutetium oxide. So the lutetium-176 enrichment is 64%. Using the trigger Puspati reactor in Malaysian Nuclear Agency. After the irradiation, the sample was dissolved in 1 molar hydrochloric acid. And before we use this product to do the labeling, the radionuclide purity was determined by the quality control department, quality control unit in my department, using the radio ITLC and gamma spectrometer. Once we are sure that the radionuclide purity is more than 99.9%, then we will use this sample to make the further study. Next, please. So how to label this lutetium-177 with the dotanol? Amount of 550 microgram of peptide in ultra pure water plus the 10 microliter of 10% ascorbic acid. Ascorbic acid is used as a stabilizer, plus 5 microliter of lutetium-177 as in 1 molar of HCl. Actually, I have tried several different amount of peptide, and I found that this is the best concentration of the peptide to be used in this labeling process. After we mix everything, we adjust the pH to 5.5 and 6 using sodium acetate as the buffer. The reaction mixture was later incubated at 100 Celsius for 30 minutes. Then the reaction cooled to room temperature. Next. So how do we assay the radiochemical purity? So the definition for radiochemical purity is the fraction of the total radioactivity present in the desired radiochemical form. So in this study, we used the radio ITLC XG method, which used a very small piece of ITLC paper using a mixture of ammonia solution, ethanol, and water as the mobile phase. And the concentration of this mobile phase is written here is 2%, 2 to 10 and 20. The ratio of this mixture. So this mobile phase mixture could separate all impurities from the labeled compound. Next, please. So this diagram just to show you how we carry out the ITLC process. So on the paper, we spot a very small amount of the final product, maybe 1 to 2 microliter, and we leave this paper inside the developing chamber with the solvent. After a few minutes, we take out this paper and we dry this paper in the oven, and we count this ITLC strip using the TLC radiochромatogram scanner. Next, please. So in order to study the stability of this lutetium-177 DOTA-TIC, after the labeling, the product was kept at room temperature for this study. So the radiochemical purity of the labeled product was continued to monitor by the same method, ITLC-SG, at the 0 hour, 1 hour, 2 hours, 3 hours, 24, 96, and 168 hours post the labeling. 168 hours is 7 days. Next, please. For the next study, we study the serum stability test. So the serum stability test was performed using the bovine serum to focus in vivo stability. So in this study, I used the bovine serum because I couldn't find the human serum in my lab. So in the next study, we will repeat with using the human serums to verify the results again. So in this study, I used 100 microliter of the lutetium DOTA-NOT and added to the 5% of the serum solution, and the mixture was incubated at 37 Celsius over 7 days. The same radio ITLC-SG method was used to determine the percentage remained intact at 0.25 hours, 1 hour, 3 hours, and 24, 48, and 168 hours. Next. So next we move to the results and discussion. So first we see the physical appearance of the label product. So the final product is we obtained a very clear and colorless solution, and we check the pH. This is a pH 5.5. Next. Next slide, please. So for the radiochemical purity assay, this is the chromatogram that we obtain. Because this 177 lutetium DOTA-NOT, they are water soluble. So in this aqueous mobile phase, for sure they will move along with the solvent front. So once we develop this compound, we develop this sample with a mixture of the solvent, the DOTA-NOT remained, the DOTA-NOT, the label DOTA-NOT will move to the solvent front with the RF value of around 0.87. And as you can see from this graph, at the origin, there is nothing remain in the origins, meaning that more than 99% of this product are 177 lutetium DOTA-NOT. Next, please. To challenge the functioning of this mobile phase, we tested with by using the ionic lutetium-177, which is the pure lutetium-177. Though we do not label with anything, so we spot on the same ITLC-SG paper, and this is the result we got. So all of the ionic and other ionic impurities, they remain at the origin and nothing move along with the solvent. And this we can conclude that this mobile phase is the right mobile phase that to separate the product and the impurities. Next, please. So the stability study of the 177 lutetium dotanol, as you can see from this table, from 0 hour, the percentage of RCP is 99.6%, and after 1 hour, 2 hours, 3 hours, and 7 days, doesn't change a lot about regarding the RCP. So this is proven that this lutetium dotanol is very stable. Next, please. About the serum stability test, which is what we challenge the in vivo stability. Also, we incubate at 37 Celsius. As you can see from this table, the percentage remained intact is still very high, from 99.3% till at the day of 7, it only dropped a little bit to about 98.6%. So there is no product degradation. We expect there is no product degradation of this lutetium dotanol in serum. Next, please. So this is the conclusion from this preliminary study. The first conclusion, the radiolabeling of 177 lutetium dotanol was successful with the radiochemical purity of more than 99%, 99.5%. And this complex also exhibited significant stability in room temperature for up to 7 days in vitro. And the serum tests also show high compound stability over 7 days. So these preliminary results demonstrated that it has great potential to be produced locally for the treatment of neuroendocrine tumors. Next, please. Of course, because this is only the beginning, we have planned for some future directions. First is to evaluate the radiochemical purity using the HPLC, because of course the HPLC is the more advanced technique for the determination of the radiochemical purities. Second is to optimize the labeling methods using higher radioactivity, such as 200 millicurie. This is almost the same activity for the patient injection. And to make the labeling process easier and convenient, we would like to develop the kit-based labeling for the easy and rapid preparation of patient doses of 177 lutetium dotanol at the hospital radiopharmacy. So to do this, we need to formulate the kit. So we find the right formula and we freeze dry the kit, and we can supply, hopefully we can supply this kit to the hospital needed. And to study in vivo biodistribution of this product using small animals as model. Next, please. So these are the references I used in this study. Next, please. So these are my acknowledgement to Malaysian Nuclear Agency for providing the funding to buy the raw materials such as the lutetium-176 oxide enriched. These are quite, the raw material are quite expensive. And also the medical technology divisions and reactor technology centers for their generous help and for providing guidance and assistance to carry out this study. Next. Thank you for your attention, and stay safe, everyone.
Okay, so thank you, Madam Ng, for your presentation. Okay, now we will continue with our next presenter. Okay, Ms. Rogama. Okay, the research titles are the effects of object to film distance to industrial radiography image. Okay, so I will be the one that presenting this papers today.
Okay.
Assalamualaikum and good evening. So now I will be presenting the research title, Effects of Object to Film Distance, to industrial radiograph image. So this is basically actually related to my final year project students. So continue. Next slide, please. So this is the contents of my presentation. We will start with the introduction, the objective of the research, the methodology, research, and the discussion, then continue with the conclusion. Next slide. So for the introductions, so we know that the quality of the radiography image is actually determined by the films or form, which is the types of films, the source to the film distance, where do we put our film is, the times and the angles of the exposure. A radiography image consists of varying shades of gray, that will appear in our films, ranging from white gray to one and to block gray to the others. The effects of the voltage also impacts the radiography image, as the energy that we use for the X-ray relates to the X-ray penetrating power. So that means to get the quality image, voltage also plays the important roles. So source to film distance is the measurements of the variations to the films to be viewed from the X-ray tubes. So this one, the film distance, will cause the change in the density and also the exposure times of the films. So then the flat panel detector that we use, also play the important roles for our image quality. Okay, because it's actually analyzed and used as the guidance for our image. Okay, image appearance. Okay, and this one is the effect is actually includes the scanning and angles, the voltage size, the reconstruction sensor, and also anti-scattered rates. Okay, as well as the resolution. Okay, that we use while penetrating our films. Okay, by using the flat panel detector, digital radiography that we evaluate. Okay, next slide, please. Okay, so this one is actually the objective of our research. The first one is we want to study the effects of the film distance, okay, to image when using the radiography testing. Okay, the second one is we want to examine the image, okay, whether we can improve by post-processing methods. Okay, so in this research, we are using the IIP console software. Okay, the third one is want to study the effects of X-ray wavelengths, the penetrating power, and also the intensity. Okay, next slide, please. Okay, so this one is our methodology. Okay, so this one is our sample preparations. Okay, we are using the wooden blocks. Okay, then after that we do the artificial defects on our wooden block, okay, by using the drill press machine. So you see here, okay, we have flat surface defects and also irregular surface defects with a difference for their defects opening. Okay, so for the flat surface, okay, the opening, the artificial defects, okay, that was done is 9 millimeter and also 15 millimeter. And then for the irregular surface, the defect is 9 and also 15 millimeter. Next, please. Okay, so this is the characterization, okay, method that we use. Okay, we are using the X-ray generator, which is model XRS4. Then we'll have our panel detector. And also we will evaluate our image by using the IIP console software. Okay, and then next. Okay, so this one is example when we tested our sample. So this one is for our flat object sample when we do the artificial defects and also for the irregular defects. Okay, so we take the film to object distance that was used in this research is we're starting from 0, 5 mm, 10 mm, 20 mm, 25, 30, and 35. Okay, so then after that, we will check the distance, okay, that we see from the image appear on our console software by using the console software. Next, please. Okay, so then we go to the result and discussion. As you can see here, okay, so this is the graph of a defect size versus the our distance, okay, for 9 mm a whole wooden block. So you can see here as we move further, okay, our object, okay, from our source. So you see here, it's supposed to be that our defect is 9 mm. Okay, but when we move forward, our object, okay, so you see here there are increasing in terms of the defect opening. Okay, so this one you see the increasing in terms of either for the flat and also irregular ones. Okay, next please. So this one also seems, okay, with the opening of 15 whole woods blocks lah. Okay, this one you see the difference in terms of the defects okay, to the flat and also irregular shape lah. Okay, so we can see that for the irregular shapes, okay, when we move the object distance, okay, there are a lots of the difference, okay, for the openings lah. Okay, supposed to be our device is 15 mm. So when we move forwards, okay, our distance, okay, so we can see our increasing in terms of the device opening. Okay, next slide. Okay, so this one, that the image that appear, okay, that we capture from the IIP console software. Okay, this one is for the irregular surface defect for 9 mm. Okay, so IIP console is actually we use to process our image lah. So for digitalized, so the openings of you can see the gray color one, okay, is actually the artificial defect that was done before. Okay, so from the opening, we can identify the distance value that we can capture previously that I show you the value. Okay, so this one is example of the opening, okay, for 10 mm defects and also the 30 mm defects lah. Okay, so you can see here, okay, from the pictures that you see the in terms of the image lah. So that's mean, okay, for the by using this IIP console software, okay, we can process, okay, our image is actually we can change, okay, the effects of the image lah, the process of our image. Okay, the intensity of our image we can control by using the IIP console software. Okay, next, please. Okay, so this one is the image that we see from the flat surface lah. Okay, flat surface detection. So you see here for 9 mm and also for the object to film's distance, okay, 10 mm and also 30 mm. Okay, so there are different in terms of the contrast of this image. Okay, so that means we can play around with the contrast of the image by using this console software. Okay, next, please. Okay, so this one is the device for the 15 mm console and also for the object to film distance 10 and also 15 mm. Okay, next, please. Okay, so this one for the irregular surface, okay, device for 15 mm artificial device. Okay, so this one is the first pictures is for the 10 mm opening, and then the second pictures is for the 30 mm openings. Okay, next slide, please. Okay, so then this is the end of my presentation. So as the conclusion from this, okay, the conclusion that can be done is that the object to film distance actually play the important roles in determining the image quality of the film. So as you can see, okay, previously from the results, okay, that was shown. Okay, and then the second one is the quality of the image actually can be improved by using the digital image processing that we use in this research is IIP console software. Okay, next. Okay, so then thank you so much. I will end my presentation here. Okay, then I will start with our last presentation. Done. Okay, so then with the last presentation, which is the developments of battery radial arm robotic system for corrosion inspection on wall reactor tank trigger. So this one also the project of final year student, okay, for unit 10. Next slide. Next slide, please. Okay, so this is the contents of my session. I will be introduction, objective, methodology, result and discussion, and also conclusion. Next, please. Okay, so then I will start with my presentations of the developments of battery radial arm robotic system for corrosion inspection on wall reactor tank trigger. Okay, this one is actually my final year project students. Okay, next slide, please. Okay, so this is the contents of my introduction, contents of my presentation. So we will start with introduction, the objective, the methodology, results and discussion, and also the conclusion. Next slide. Okay, so for the introduction, we know that the ultrasonic is actually one of the most common NDT methods and also is a non-invasive diagnostic in industry of non-destructive testing. Okay, so the ultrasonic testing use the methods of a high frequency sound wave that are above the range of human hearing to measure geometry and physical properties in materials. Okay, so there are many application or inspection that we can use the ultrasonic testing. So for example, we can use for the fault detection, okay, the evaluations, dimensional measurement, material characterization, and so on. Okay, next please. Okay, so ultrasonic information, this one is actually can be obtained and presented in various size. Okay, there are three most popular formats that we can use is A scan, B scan, and also C scan presentation. Okay, but in our project, okay, in our research, we will use C scan presentations. Okay, next slide, please. Okay, this is the objective of our research is actually to design and upgrade existing scanner of battery radial arm robotic system for corrosion inspection on wall tank trigger with two key features. Okay, the first key features is the reliability can be described as a complete range of reliable and high performance ultrasonic system for reactor tanks The second one is the customization. So that means we design the ultrasonic probe for rectal tank that will allow upgrading, okay, easily matching dimensional, kinematic, and technique related to specification. And then the second one, okay, is to demonstrate a simulated scanner design for underwater inspection environment verifications. Next slide, please. Okay, so this is our problem statement. So the research is actually we will focusing on the mechanical designs, okay, of specific NDC method for underwater inspections of the full linear in the reactor. Okay, for this we choose the ultrasonic with a C-scan emission methods lah. Okay, and we also follow the lamp wave techniques, thickness mapping. Okay. However, there are serious challenges in applying ultrasonic testing because of the existing system limit to large user that not suitable for underwater application, especially for the reactor tank. So that's why, okay, we will develop the new battery rather that we actually improve from the existing one. Next, please. Okay, so this is our methodology. The first one, we check the requirements, okay, which is data collection. So we will collect the data, okay, from the reactor. So we will check the conditions of the reactor, the work times of the reactor, okay, and then we collect the data from the existing robotics arms, okay, that developed previously. So either we how to make the improvement from the existing system. Okay. After that, software requirements. Okay, we will use software to simulate this system that we have done. Okay. So after that, we will design our sketch, okay, by produce the draft sketchings of our product designs. Okay, after we produce the sketch of our product design, okay, we will discuss first which design is actually the most suitable and applicable for the UT. Okay, and then after that we finalize our design. Okay, next please. Okay, so this one is the data that we collect. Okay, so the reactor diameter, the height of the reactor, the thickness of the walls, and the clearance on the tanks. Next please. Okay, so this one is the pictures of the top view and also the wall underwater reactor. Okay, for our reactor. Okay, then next. Okay, so this is examples of the existing probe and also the system. Okay, so the first picture is our probe holder. Okay, the second picture is gantry radial arm system. And then the third one is actually our ultrasonic inspections. Okay, so we have a problem for the existing system, which is it's not suitable. It cannot change the angles of our ultrasonics and also, okay, the movement is limited. So that's why we need to improve the system that we have. Next, please. Okay, so this one is existing probe. Okay, next. Okay, so this one also the existing probe system that we have. Okay, next. Okay, next. Okay, then we will continue with result and discussion. Okay, so this is our finalized design that we finalized after considered all the factors. Okay, so this one is actually the multi-view of our final design. Okay, and then this one is the second pictures is the multi-view of our final designs of the rock holder. Okay, next. Okay, so this one is finalized design when we draw, okay, by using the software. Okay, this one is for our roller, and then this one is our rock holder. Okay, next please. Okay, so this one is when we do the simulations, okay, for our UT. Okay, so for the improvements of this, okay, actually we are using the X and Y at this. So that means it will rotate, and it's actually easier to change the angles. Okay, so next please. Okay, so this table one is actually the different in terms of the existing and the new battery radial arm system that we developed. Okay, so you see here the movements of the system. Okay, the existing one is actually very limited. Okay, so the new one, okay, the system that we designed, okay, free moving, as we actually we use the X and Y axis. Okay, so then the in terms of the assembly, okay, so the assembly in terms of the existing ultrasonic instructions, okay, the existing one is using a slot pin. Okay, so it can be removed easily. Okay, and then the new battery that we developed, okay, is a friendly user. Okay, because of the roads that we developed have a track that can be easily detached. Okay, the maintenance is low compared to the existing one. Okay, next. Okay, so this is the before we finalize the designs. Okay, so this is the analysis that was done. Okay, so we do the stress and strain analysis first. Okay, so you can see here. Okay, this is the stress and also the strain analysis. Okay, based on the results, okay, from the deformation scale, okay, the stress analysis that we get from the software is 6.045. Okay, so this value, okay, is to ensure the results of lines can be met with whether the design has been created and also built. Okay, so after we do the stress analysis and also the strain analysis, okay, so we may identify either this design is suitable or not. Okay, based on the result, okay, stress and strain analysis, this design is suitable for our battery arm. Okay, next please. Okay, then we done the buckling test. Okay, so from the result, the deformation scale was 9.23112. Okay, so when we slot in our UT inside the reactor tank, okay, so the result shows that we will not have bucklings. Okay, even though because we know that no buckling in our roots. Okay. Next, please. Okay, this one is the safety factor. So we also have to calculate the safety factor of our roads. Okay, so the safety factor is defined as the material output stress divided by effectiveness stress. Okay, of 1 meters for aluminium material use. Okay, so in this project we are using the aluminium 6061. Okay. So our material safety factor, okay, after calculate is 1.9. Okay, so it's ranging from a low value because the value for the safety factor is range from 1 to 100. So that's mean from this value we know that our road is actually safe to be used lah without failure in terms of the fabrication. Next, please. Okay, so because we know that in our reactor pools we have a water inside, so we cannot ignore the buoyant force. Okay, so then we have to we calculating the buoyant force of our robotic arm. Okay, so we are using the formula, the buoyant force formula to calculate. So we take into account, okay, the material that we use in this project, which is the aluminium 60661. Okay, so from the calculation, okay, so that the value that we get, okay, we know that our force, okay, is more than the buoyant force of the water. Okay, so that means we know that our road will sink into the water lah. So that means it will not float away when we want to measure the corrosion for the tank wall. Okay, next please. Okay, so then for the conclusions, okay, after we measured all the safety precaution, okay, so the design was approved and safe to be used, okay, with the factor of safety of the roads that we calculated previously is 1.9, and it's also user friendly, okay, and it's easily to assemble and also when we do the stress and strain testing. Okay, so then we can conclude also, okay, the guthrie radial arm that we designed, okay, the function is good and also it's affordable with a low maintenance. Okay, so and then all the new develops the new guthrie radial robotics arm that we develop is good to replace the existing arms that we have previously. Okay, next please. Okay, so thank you so much. Okay, so then with the ends of these presentations, okay, we already at the ends of our session for the afternoon. Okay, so then I will close our session today. Okay, and on behalf of the organizing committee, okay, I would like to say thank you for those who join our iNuSTEC 2020, okay, either by using the WebEx or YouTube. And then stay tuned. Don't forget that we have the last day tomorrow. We will have the debate nuclear. Okay, so there are very exciting, okay, debates from the university, which is in UNITEM, UKM, and also UTM. Okay, so with this, I will end our session today. So thank you so much and see you guys tomorrow.